Okay, great. So it's a great pleasure to welcome Nima Arkani-Hamed from the IIS. So originally we arranged Nima day tomorrow, but now we also have slots today, and he kindly agreed to actually start early today. So I guess the first session will last for around 3 hours before we take a break, but maybe we can also take small breaks in between if needed, and you can interrupt anytime, I guess, or raise questions or just raise questions in the chat. Okay, so let's welcome Nima to give the first lecture on scattering amplitudes and positive geometry at infinity.
All right, guys. Well, it's really wonderful to be able to join you and give these lectures. I'm actually grateful to have the extra slots so I can give a somewhat more complete and hopefully pedagogical overview of some of these ideas. Let me begin with a quick overview and context for what we're going to be talking about. We're going to be talking about scattering amplitudes, obviously. Okay, so as I said, we've known really since the 1960s that that in quantum gravity we can't have any observables in the interior of space-time, and so the only kind of observables that we can meaningfully talk about, quantum mechanical observables that are precisely defined, we can meaningfully talk about, are anchored to the boundaries of space-time. And in the 60s, this was really first appreciated by people explicitly or implicitly, like Bryce DeWitt and Roger Penrose. And in asymptotically flat space, the observables that people talk about that they decided to start focusing on were indeed scattering amplitudes, because scattering processes are things where this is the Penrose diagram for flat space. Scattering processes are exactly things where we shoot particles in from minus infinity and they go out. Something happens in the middle, and some particles go out and they're measured at plus infinity. Of course, many years later, we've learned to focus on this sort of with this holographic mindset about quantum gravity, about asymptotically anti-de Sitter space. And here, the analog of the boundary observables aren't scattering amplitudes. Here, there's an even richer array of objects that we could be talking about, where we just ping the walls of this box and of this asymptotically anti-de Sitter cylinder. And again, we would imagine that what's really happening if we did that was sort of waves go in to the middle of the space and sort of crash into each other and they come back out. Yeah, so we're by now very used to the idea, this deep and wonderful idea, that in asymptotically anti-de Sitter space, that the observables, the holographic observables we're allowed to talk about, the boundary observables that we're allowed to talk about are correlation functions, and that in fact there's a theory that lives on the boundary of anti-de Sitter space that calculates holographically these observables that naively, as a sort of bulk gravitational person, you think you need all of the interior of the anti-de Sitter space to describe and compute. Now, and so this is our sort of first example of what the idea of emergent space-time from more primitive degrees of freedom might look like, but it's actually an example of emergent space and not emergent space-time. So the reason is that we're leaving time alone. Time flows up on the sides of this anti-de Sitter space tin can, exactly the same as it flows in the interior of the anti-de Sitter space tin can. And related to that, the theory on the boundary is a normal theory that we have words to describe, a normal quantum mechanical theory. In fact, so this is an example of something that you can think of as quantum mechanics or quantum field theory as sort of being king, and emerges from it space and gravity and strings and all these other amazing things that people have been studying for over 20 years, and people will be studying for many more years. But it's not the real world. As we start trying to get closer to the real world, in fact, we can go back to these earlier observables. Flat space is one step significantly closer to the real world. Of course, the real world isn't even in flat space, it's cosmological. But already going to flat space and talking about the observable of the S matrix, we have to confront an essentially new issue of time. So these observables are ones where we can't ignore the sort of dynamical aspect of the problem. In a sense, we can sidestep that issue at the sort of deepest level. We can sidestep that issue when we talk about asymptotically anti-de Sitter space, because we can talk about the Euclidean version of these theories, where the theory on the asymptotic boundary is then a Euclidean conformal field theory. And then the rules of consistency for what the consistent boundary observables look like are the same as the rules of consistency for a Euclidean conformal field theory, which are while we don't know how to solve for the consistency conditions for all possible conformal field theories, and that's the whole conformal bootstrap program to try and do that. If someone claimed to give you a set of correlation functions for a Euclidean CFT, you would know exactly what to check if they were right or wrong. You would check that the correlation functions only have singularities once points collide, and that the singularities satisfied appropriately the operator product expansion. This has to do with the fact that the boundary of anti-de Sitter space, even Lorentzian anti-de Sitter space to begin with, is a normal place. That's just what we stress. It's a normal place. It's a normal space-time. It has a notion of, it has a metric. It has a notion of locality. It has a notion of time evolution. And therefore, by analytic continuation, by Wick rotation, we know that we're supposed to be able to get all of those things from the properties of a Euclidean conformal field theory, where the rules of that beast, while difficult to satisfy, and we don't know exactly the space of all solutions, the rules are perfectly well defined. By contrast, when we're talking about asymptotically flat space, the situation is totally different. There, the boundary of flat space is a much less familiar place. What is the boundary? Well, there are lots of ways of talking about the boundary of flat space. For example, the most obvious thing you could do is look around to see what you see in the sky, and you see a celestial sphere surrounding you. So that's a relatively obvious place where you might imagine looking for a holographic theory. But once you go there, it's not much there. It's just a two-sphere, and maybe there's a notion of an affine or null time at infinity as well. But this is already a much less familiar place. It's not at all obvious that there's any notion of locality, for example, on that celestial sphere. Similarly, there's nothing especially special about that description of the boundary of flat space. In fact, we can kind of say what our issue is, or what the challenge is, a little bit more, a little more generally. We have some scattering process, and it's labeled. It has just the data that labels it. There are many ways of talking about the data that labels it. To begin with, let's just say that we're labeling it by the momenta PA mu, and let's say I'm talking about massless particles. Let's say the momenta and the helicities of the incoming particles. These momenta are on shell, so p squared is equal to 0, and that's our data. That's what labels the scattering process. And you can think of many ways of sort of describing this on-shell kinematical data. One of them we just did in terms of null momenta. We can do it in terms of, as we'll talk about in a second, a twistor or momentum twistor variables. We can, let's say we only have scalars. We can do it in terms of Mandelstam invariance. These are just different ways of talking about just specifying the data of the actual scattering process. We could talk about the celestial sphere as a geometrically particularly natural way of doing it. But anyway, this is our canvas. This is the canvas. And in none of these spaces is there any sort of clue of what kind of theory you should be talking about. For example, if someone just hands you n null momenta, what are we supposed to do if we want to have this kind of holographic mindset? We want to ask a question in the space of n null momenta, whose answer gives us the scattering amplitude with all of its richness and complexity. And how are we supposed to do that? Similarly, with any of these other ways of labeling what the actual data of the scattering process is. So that's the question that we're going to be looking at for these lectures. In other words, if you just imagine that here we are at infinity. Imagine that we're some experimentalists at infinity. Here we are at infinity, and we throw the particles in, and we measure them when they come back out. Or we're going to imagine a slightly more theoretically friendly experimentalist, where all the momenta are drawn as incoming. But anyway, we do the measurement at infinity, and we want to know what gave rise to this sort of complicated pattern of processes that we ultimately measure as the squares of these amplitudes. And the conventional picture for what's happening inside is the conventional picture for what's happening inside. Yeah. So the conventional answer is that what's happening inside is that we have some particles coming in, they bang into each other, and we sum over. These interactions are local interactions in space-time. So we're supposed to sum over all pictures, and this makes the locality in space-time manifest. And we make unitarity manifest, or quantum mechanics manifest, by summing over all the diagrams. That's Feynman's picture for what's going on, even in perturbation theory. But this conventional picture is exactly putting in a large auxiliary space, which is not part of the definition of the problem. So the interior of the space-time. The interior of the space-time is a large auxiliary space, which is not part of the problem. Even the Hilbert space, in which this unitary evolution is taking place, is auxiliary, is not part of the definition of the problem. And so we would like to do something else. So we really want to ask a different question. That's what we're looking for. We're looking for a different question that we can ask without this auxiliary structure in it, whose answer is still going to give us exactly the same, answers, but without putting in the interior of space-time or any sort of manifest picture of unitary evolution in a Hilbert space. So that's our goal. We want to find there's going to be some new physical ideas and some new mathematical structures. So if we're going to sort of chuck unitary evolution and local interactions in space-time manifestly, we're going to chuck that, but still get exactly the same answers out. There has to be some hefty structure there, which replaces it. Again, there's no obvious roadmap for how to proceed. So this is not like the, once again, it's not like the situation that we've gotten used to in ADS, where we know exactly what the rules are. So this is a basically more adventurous and risky enterprise. Okay, we don't know exactly what we're doing. We don't know what the rules are, but we have one huge guide to helping us do this. We have a kind of theoretical experimental data. We know in the end, if we're going to get the answers for these amplitudes from some whiz-bang new point of view involving new questions in mathematical structures or whatever at infinity, that we had better reproduce exactly the same answers that we would get for more conventional means. And in particular, we know how to check, at least in perturbation theory, and I'll talk about this a little more, especially at the level of the so-called integrand of the scattering amplitudes. We know how to check if someone does the calculation. They said they sum over all the Feynman diagrams and they got the answer and they hand them to you. We know how to check if they're right or wrong. There are checks that we can do on these very rich and complicated, but ultimately rational functions. There are checks that we can do on those functions to see if they're local and if they're unitary. And the checks have to do with the singularity structure of these functions. Roughly speaking, locality tells you where the poles of the scattering amplitude should be, and unitarity tells you what happens as you approach those poles. That we have to have certain kinds of factorization for the amplitudes as we approach those poles. So we can check if something is right or wrong, if something agrees with the principles of locality and unitarity. And so what we're looking for is a substitute for evolution in space-time and evolution in Hilbert space for guaranteeing those principles. And of course, the hope is that if we understand, if we start at least grasping what, getting some examples and having some feeling about what these new principles and ideas might look like, they might ultimately give us the correct grammar, the correct language to talk about the more primitive constructs out of which not just space, but space-time might emerge. And in fact, what I think we're seeing in these examples is rather than quantum mechanics being king and having space emerge from it, we're beginning to see some other set of ideas, exactly the same question mark, and out of which we can start to see in baby steps, but really quite concretely, we can start to see space-time and quantum mechanics emerge together, somehow joined at the hip. Okay, so that is the rough introduction. Maybe I can stop and ask for some questions at this point. Any questions? Just on this rough philosophy before we start?
Yeah, I have a question, Nima.
Yeah.
What is this set of momenta that you, and helicities that you sort of mentioned in a cosmology? What would you consider as the input data from which you want to?
That's part of what we're going to be seeing. Again, just to stress again, this is kind of an experimental theoretical subject. So we don't know we don't know exactly what the rules are, and we're experimenting and looking. I mean, the most obvious thing is the most obvious data is just n on-shell momenta and specifying whatever representation of the little group that is involved with the scattering process. Particles massive, massless, whatever. That's what we could be talking about. And again, there are various ways of coordinatizing that, and they can all be sort of transformed to each other. So I don't see any especially deep difference between different ways of talking about it. One interesting thing that we'll be seeing. So today, so just to just to give the sort of plan for the 2 days of lectures, today I will be talking about the scattering amplitudes of gluons and their generalizations in n equals 4 super Yang-Mills. And there, the kinematic space is really going to be almost directly the space of n null momenta for the external gluons. We're going to find it convenient to parameterize that space in terms of the so-called momentum twistors that Mark Spradlin introduced at the end of his lectures, and I'll briefly review. But that's basically for every particle, there's going to be a 4 vector. You could think of it as a null 4 vector, and we'll slightly transform it to think about a 4 vector up to rescaling. So a point in P3. So that's 3 degrees of freedom, correct counting, 3 degrees of freedom for every external particle. And as we'll see, we will be able to describe the helicities of the particles in an interesting sort of new geometric way already directly in that momentum twister space. And in fact, the attitude we're going to take towards thinking about the amplitudes there, we can directly apply even to the standard model. And an important idea is going to be that we're going to see all these, we're going to think about scattering amplitudes actually as differential forms on this kinematic space. So now in this story, where in the story of n equals 4 super Yang-Mills, that's our kinematic space. That's our canvas. It's the space of n null momenta, or the n momentum twistors. And we're going to find this positive geometry that lives in that space. And that's the story of the amplituhedron, and that's what I will talk about today. Tomorrow, we'll switch to talking about a much more general set of theories, totally non-supersymmetric in any number of dimensions and so on. And the story today will be about n equals 4 super Yang-Mills, also in the planar limit. Tomorrow, we'll be talking about arbitrary theories, arbitrary scalar theories, really something that has to do with the universal singularity structure of really any theory, but really specifically this colored scalar theory, the so-called bi-adjoint scalar theory. And there it'll have nothing to do with, there's no supersymmetry, there's no planarity. We'll be talking about a large N expansion. We'll be talking about a genus expansion ultimately. But it's true. What we'll be talking about is meant to be valid to all orders in the 1/n expansion. And there, the natural kinematic variables we talk about will not be associated with one particle at a time, but will be associated with 2 particles at a time. It'll be associated with Mandelstam invariants. So our kinematical space there is going to be rather different. It's a space of Mandelstam invariants. But again, the same kind of philosophy is going to, that we're going to see the same kind of philosophy in action. We're going to see a certain kind of geometric structure in the kinematic space, and we're going to ask some natural questions in that space, whose answer gives us, is going to give us the amplitudes. Does that answer your question, Spencer?
Yes, yes. Thank you.
Okay, great. Okay, so all right, so let's go back. Okay, so okay, so so now let's get down to a business. So I'm now going to be speaking about the kinematical space for n equals 4 super Yang-Mills. And to begin with, remember, I'm just reviewing things that you learned from Mark's talk. We can think about null momenta. Okay, so we can think about null momenta and we associate them with these spin and helicity variables. And this makes the fact that p squared equals 0 is manifest. Okay, so the fact that p squared equals 0 is manifest, but momentum conservation is not manifest. So in other words, these variables are still not unconstrained. I have to further impose momentum conservation, or momentum conservation is a fact about this data. So the sum of lambda a alpha lambda tilde a alpha dot equals 0. Little a is always going to be an index that runs over all n particles for me. So okay, so okay, and and in a totally general theory, this is close to the best that we can do. But in a theory with colored amplitudes, in a theory with color, like just gluons or n equals 4 super Yang-Mills, we can do a little better. And the reason is that when we think about the color structure, there's the sort of usual dependence on the color indices on the outside. Let me call these capital A's to distinguish them from the little a's that I just introduced. So I have from capital A1, capital A2 to capital AN. And we know that I can write the amplitude, which depends on some helicities and some momenta, lambda and lambda tilde. But it also has some color indices, MA1 through AN. And we know that we can write this as a sum over permutations. This is the color trace decomposition, permutation sigma of the trace of the generators A sigma 1 up to A sigma n, now multiplied by something which no longer has the those color indices, but which depends on this permutation. So I can think of this then as an amplitude that just depends on each one of these partial amplitudes inherits the ordering that we see in these colored traces, A sigma, lambda tilde, A sigma. And in the planar limit, we're only interested in the single trace terms. At tree level, we only have single trace terms anyway. At loop level, we're only going to be interested in these in the pieces with one trace at leading order in the large N expansion. So that means that each one of these pieces has the external particles ordered in some way. So that's going to be an important idea, is that there's actually an ordering associated with them. And this ordering is quite important. As we'll see, it's the beginning of the tiny bit of structure that we can add to this kinematic space that many things are going to flower from. So in other words, we can now think about the amplitudes as really associated with like H1, lambda 1, lambda tilde 1, and so on, Hn, lambda n, lambda tilde n, where we have this 1, 2 up to n as a cyclic ordering. So there's still so if there's still a cyclic ordering, because the traces, of course, are cyclically invariant. And that means that we can, it makes sense to draw the momenta end to end on a d-dimensional piece of paper if we wanted to, okay? So because there's an ordering, it makes sense to draw the momenta like this. If there wasn't an ordering, it wouldn't be obvious, obviously, how to put one after the other. But with an ordering, we can do this. And so now this picture makes manifest that we have momentum conservation, because momentum conservation just tells us that this forms a closed polygon. So and so we can think of each one of the momenta, each PA, as actually as given by the difference between the coordinates of the vertices in this in the space in which I'm drawing. Okay, so this would be x2, x1, x3, and so on. Okay, so so this picture of the null polygon this makes momentum conservation manifest. But the fact that the sides of the polygon are null is not manifest. Okay, so what we want is a set of variables that makes everything manifest. So this is just a simple motivation for it's a simple just a practical motivation. We want to sort of label the scattering data in the cleanest possible way, where we don't have to put any external constraints on them. And this is what momentum twistors buy for us. So Mark talked about this quickly, but let me just say a little bit about it again. So the twistor aspect here has to do with conformal symmetry, and in fact, there's going to be the amplitudes we're interested in are going to end up having this fascinating dual conformal symmetry, this conformal symmetry in momentum space, which is distinct from the conformal symmetry in ordinary space-time or ordinary momentum space that we know they have. This is a hidden symmetry. It's fascinating that it's actually a hidden symmetry that, at least at tree level and at low orders in the loop expansion, is there for any a maximally supersymmetric theory in any number of dimensions. So it's amusing that this hidden symmetry is there in any number of d greater than or equal to 4 dimensions, while the obvious conformal symmetry is only there in 4 dimensions. But let me just take a moment to motivate just this way of thinking about conformal symmetry, this sort of twistorial way of thinking about conformal symmetry in 4 dimensions. So something that you know very well is that if we have 2 points in space-time, well, let me actually say, let me back up it one second. There's something a little bit funny about the way we talk about space-time symmetries. When we make space-time points, the stars of the show, which is normally what we do in textbooks. What are the symmetries that we're used to thinking about in space-time? Well, there's translations, and translations look like I'm being loose here. Translations look like d by dx. Then we have things like Lorentz and rotations. These look like x ddx. And finally, we have special conformal transformations that look like xx ddx. And it's a little bit peculiar that despite the fact that all of these generators are sort of unified and combined together in the conformal group, or even for that matter, these guys are unified and combined together in Poincare. And then we have for the full conformal here. It's a little bit strange that they're treated on a rather different footing. They're different looking generators. The situation changes very beautifully if instead of thinking about points in space-time, you think about null rays in space-time instead. So so let's say I have a null ray in space-time. Well, first, what's special about being null? Well, if I have 2 random points, x1 and x2, then the difference between them, x1 minus x2 squared, let's say they're not null separated, then this isn't, of course, it's not conformally invariant. It's not even invariant under dilations, but in particular under inversions, which is the exciting part of the conformal group, the very non-trivial part of the conformal group, under inversions, x1 minus x2 squared goes to x1 minus x2 squared over x1 squared x2 squared. So of course this is not invariant. However, if the points are null separated, if x1 minus x2 squared equals 0, then it is invariant. In other words, whether or not two points are null separated is a conformally invariant notion. So that tells me that if I have a whole null line here, I can do a conformal transformation on it, and it'll go, maybe it'll change, the points will move around, it'll go to another null line. Okay, so null lines are invariant. Well, they're not invariant, but they map to null lines under the conformal group. And so that's an invitation to try and think about everything instead of using space-time points, to thinking about these null rays instead. Now, how do we think about these? Null rays? Well, let's imagine that I have 2 points, x1 and x2. And I'm going to use the 2 by 2 matrix notation for them. And let's say that they are null separated. Well, if they're null separated, what does it means that x1 minus x2 squared is 0, but in this language it means that the determinant of x1 minus x2 is equal to 0. But that means that x1 minus x2 has a null, x1 minus x2 has a null space. So I'm going to say that it has some 2 vector lambda that annihilates it. Okay, that is annihilated by it. And so that means that therefore x1 alpha 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 dot lambda alpha is equal to x2 alpha alpha dot lambda alpha. And so what I'm going to do is say that that I can associate this null ray. Since this is true for any 2 points, any x1 and x2 on this ray, every point on this null ray is going to satisfy that x alpha alpha dot lambda alpha is the same. They're all equal, and they're all equal to the same thing that I'll call mu alpha dot. Okay, so this is an efficient way. This is a very nice way of specifying a null ray in space-time. Null ray in space-time are points x that satisfy this equation. So in other words, the data that specifies a null ray is giving me a lambda and a mu. Okay, so I'm going to group that lambda and a mu into a 4 vector. Just like Dirac spinors. Okay, so I'm gonna I'll call this a lambda alpha and a mu alpha dot. I guess I'm slightly changing my notation, so here I would write down x alpha alpha dot lambda alpha equals mu alpha dot. Okay. So far, we haven't even seen anything about conformal symmetry yet. This is just a nice way of talking about. A null ray. So I'm grouping them into this 4 vector. But now we have a nice observation. First of all, how do the Lorentz transformations act? Well, Lorentz transformations act like, lambda dd lambda and mu dd mu. So Lorentz transformations just act like one SL2 up here and another SL2 there. Okay, so Lorentz transformations act like linear transformations. Okay, we're familiar with that. That's part of the magic of working with this alpha alpha dot notation. It makes the fact that the Lorentz group is just simply linear transformations manifest. that's already kind of interesting. You know, in general dimensions, the Lorentz group is, you know, is O d minus 1, 1. It's a special fact about 4 dimensions that's equivalent to SL2 cross SL2. SL2C in Lorentzian signature and SL2C cross SL2C, 2 copies of SL2 for general complex momenta. That fact that it acts like linear transformations is a clue that it's something more interesting and more simple is happening in 4 dimensions. And that extends to the whole conformal group. Let's actually see how the translations act. So translations send x alpha alpha dot to x alpha alpha dot, let's say, plus some translation, I don't know, t alpha 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 dot. But you see, using this so-called incidence equation, we see that that's just taking mu and shifting mu goes to mu plus t alpha alpha dot lambda alpha. Okay, so so we see that also translations look like linear transformations, right? Translations are shifting mu by something proportional to lambda. So translations sit down here as linear transformations. And finally, the most magical thing is if we take this formula, x alpha alpha dot lambda alpha equals mu alpha dot, and I just multiply by the inverse of x, then I get that lambda alpha equals x inverse alpha alpha dot mu alpha dot. And so you see that under the inversion, x to x inverse, we simply interchange lambda and mu. So that shows us that, that the full conformal group acts as SL4 on this z variable. Okay. So I have an SL2 of Lorentz here, the 2 SL2s of Lorentz, I have translations, and I have the special conformal transformations live in this other block. So once we decide that we're focusing on null rays in space-time, then what labels those null rays? So let's go back now. So what's the data that specifies a null ray? Is giving me this z, which is a lambda and a mu. Sorry, let me. But notice that this formula, the incidence relations, x lambda equals mu, this would be the same. This would give me exactly the same equations for x if I just rescale lambda to t lambda and mu to t mu. X would be the same. So what specifies a null ray is not just zi, but a zi identified with t times zi. Okay, so these z's live in a projective space, and we'll be talking a lot more about projective geometry in a little bit. But we have this P3 and a point here in P3. So this P3 is called Twistor space. And we've seen that here are points in P3, a Z here, which is lambda mu up to rescaling. We see that if this is a point in Twistor space, that it corresponds over here to a null ray in space-time. Okay, and that the conformal symmetry acts, and the conformal symmetry is just SL4. Okay. Now, we can complete this dictionary in the following way. Sorry, I don't know why this thing keeps popping up here.
Sorry, Nima.
Yes.
There's a question in the chat asking,
yes.
can this formalism be generalized to null geodesics?
Can the formalism be? Well, yes. In some sense, the sort of gravitational part of the Twistor program was to figure out how to include thinking about curvature in the bulk with some success, but still a number of open problems. Roughly speaking, self-dual solutions of Einstein's equations in the bulk are very easy to treat with twistorial ideas. But general solutions of Einstein's equations in the bulk, well, that's kind of one aspect of that question is thinking about even gravitational scattering amplitudes in twistorial language, and that was sort of one of the sort of famous problems that they were grappling with in the 60s, and there's been some new progress on in the last decade, but it's not. But it's research. It's work in progress. Let me see what some of the other questions are.
No, I think that's it.
Okay, great. All right. Okay, so okay, so let's so we've seen that we've seen that that a point in P3 twistor space is the same as a null geodesic as a null ray in space-time. Now let's ask a different question. Suppose you give me two points in the twistor space. Let me say there's a point Z1 and a point Z2. So this is associated with a null ray. This guy is associated with a null ray. That guy is associated with a null ray. So it's natural to ask if there are points in common to these two null rays. And the first one is X alpha alpha dot. Let's say is associated with lambda 1. And the next one is associated with lambda 2. So you see that this is a total of 4 equations for the X alpha. So the sort of free variables in these equations is alpha dot. So there are 2 equations here. There are 2 equations here. So I have a total of 4 equations that I can use to solve for the X alpha alpha dot. Okay, so there is in fact a unique point in common between these 2 null rays, and the solution you can label with 1 and 2 is just mu alpha dot is lambda alpha 1 mu alpha dot 2 minus lambda alpha 2 mu alpha dot 1 over this the contraction of the lambda 1 with the lambda 2, contracting with the epsilon symbol. Okay, so we see that given 2 points, so given these 2 points in twistor space, there's a unique point X alpha alpha dot that goes along with them. But in fact, there are many such points that give me, there are many such points Z in twistor space that give me exactly the same X alpha alpha dot. We can see that from these equations because I can do any 2x2 linear transformation. I can mix these equations up. I can take any linear combination of these equations, and that will give me the same. That will give me the same X. So we see that it's not Z1 and Z2, but in fact, any linear combination, alpha Z1 plus beta Z2 and gamma Z1 plus sigma Z2, these give me, these 2 sets of Z's give me the same point. same point in space-time. And again, we'll be reviewing projective geometry sort of 101 in a bit. But what we can see already from here is that it's not just the 2 points, but in fact it's a line in P3, a line in the twistor space, and I can choose two representatives of it, two representatives of the line, Z1 and Z2, but I can choose any two that I want. Here's Z1 prime and Z2 prime, any two representatives I want. It's really this whole line in twistor space that corresponds to a point X in space-time. All right. So if I summarize the sort of twistor correspondence, we have P3 twistor space, and we have space-time, and we have that a point Z, lambda mu, point here maps to a null ray, and a line, conversely, a line in twistor space maps to a point X. Okay. Which I can, if I want to label it with 2 points A and B on the line, I can label it like so. All right. So this is purely kinematics, nothing else. It's purely kinematics. And so yeah, let me pause to see if there are any questions about this. So there's a question that points in space-time correspond to lines in P3. Does this mean that the locality is not manifest? Absolutely, it means that. This is one of the things that we're going to have to see. This is one of the things that we're going to see sort of come out of the objects and the ideas that we're talking about, and you'll see very precisely what this is about. In fact, I'm coming to this point in just a bit. Okay. All right. So let's now go back. Let us go back and look at our kinematical data. So remember, our kinematical data we decided to associate with this null polygon. The side lengths are P1, P2, up to Pn, and so we can associate these with points in this way. Okay. Now, here's the idea. We want to make manifest that we have this polygon where the edges are also null. Okay, so that's what we're trying to make manifest. The polygon makes it obvious. The polygon makes it obvious that we have momentum conservation, and we also want to make it obvious that the edges are null. So let's think about what this picture would look like in twistor space instead. Actually, before I get there, I want to mention one very important point. I apologize. In twistor space, in this P3, there is no metric. There's no notion of distance. There's no metric. In fact, the full symmetry we have, the conformal symmetry, is SL4. The only invariant tensor if the points we had are Zi, where I runs from 1 to 4, the invariant tensor is epsilon ij kl. There's no metric. The only things that we can talk about, therefore, it's projective geometry. So we're doing projective geometry. And that means that the only meaningful questions are incidence relations. For example, let's say that we have two points in space-time. So here's a point x1 mu and a point x2 mu. And then let's say they're not null separated. Well, what does that mean in twistor space? Well, x1 is associated with some line. So here's, so this is in space-time, this is in twistor space. x1 is associated with some line, x2 is associated with some other line. Oops, not drawing the line well. This is supposed to be a line. So we just have two random lines. Again, we're going to be reviewing how to, practically work with projective geometry in a little bit. But for the moment, you can just visualize all of these things as just in an ordinary real three-dimensional space. So these are just two lines. They have nothing to do with each other. Two random lines in a three-dimensional space. And there's no notion of distance. There's no notion whether the lines are close or far. Nothing, right? We don't have. There's no metric in this twistor space. However, if the points are null separated, if x1 and x2 are null separated, so x1 minus x2 squared equals 0, then that does have a meaning. That means that the corresponding lines intersect each other. And so there's no notion of distance. We only have incidence, but we have this notion that the line associated with 1 and the line associated with 2, they actually lie on the same plane and they intersect each other. Okay. That's why we're going to have to get used to, for this and many other reasons, we're going to have to really get used to living comfortably in projective space, and that's what we'll be talking about after I finish with these comments. But keeping that in mind, let's go back to our picture of the null polygon. So this is what the picture looks like in space-time. And now I want to just think about what it looks like in twistor space. And by the way, the reason for the moniker momentum twistors or dual conformal invariants is that this space-time is no longer our ordinary space-time, right? This is the funny space-time in which coordinates have units of momenta. This is the funny space-time in which I've drawn this null polygon. So these coordinates x have nothing to do with the x's that we think of as local coordinates in ordinary space-time. They're dual coordinates for this dual space-time in which I've drawn this null polygon. Okay, so that's why this the corresponding twistor space is called momentum twistor space, to remind us of that fact. Okay, but anyway, let's look at this first point x1 here. Okay, that's a line. So this is the line that corresponds to the point 1. What about 2? 2 is some other line. Okay, sorry. Well, 2 is some other line. But because 2 is null separated from 1, we know that that line intersects 1. So here's the line 2, here's a line 3, 4, okay? And so we see that the picture of the null polygon in this picture of the null polygon in space-time turns into a picture with a bunch of consecutively intersecting lines in twistor space. But now the punchline. How do I label this configuration in twistor space? Well, I can uniquely label it simply by giving these intersection points. Okay, oops. Okay, so if we take these let me draw this again. This is the null polygon. And it corresponds to these mutually intersecting lines. Okay, so I can uniquely label them by these intersection points. Z1, Z2, up to Zn. And now we've accomplished something. If you just freely give me these n four vectors, these nz, z1 through zn, that free choice with no constraints on them, given the z1 through zn, I can reconstruct, given the z1 through zn, I can reconstruct this picture of the null polygon in space-time. And concretely, that means that there's a formula, there's the following lovely formula that gives me data that's guaranteed to be null and conserve momentum in the following way. So if you give me all the ZA are lambda A and mu A, then I'm going to construct from this I'm going to construct null momenta PA as lambda A, lambda tilde A, where the lambda A is of course just given by the lambda A of the Zs, but there's a formula for the lambda tilde A, alpha dot, given by, and I think Mark wrote down this formula, but it's given by A minus 1A mu A plus 1 plus A plus 1, A minus 1 mu A plus A plus 1 mu A minus 1 divided by A minus 1A, A plus 1. This is just a perfectly straightforward exercise using the definition that I gave you for the x's, just using the incidence relations, the things that we just talked about, for going from the data of these mutually intersecting lines, going from this data to the null polygon. It's a simple concrete formula that lets you go from, let me just say it again more cleanly. So our kinematic space is, Z, you can group it into a 4 by n matrix, Z1 through Zn. The Zs are lambda A, mu A. The Zs are projective, so we can rescale each one of them separately. And out of this, we can construct PA equals lambda A, lambda tilde A, alpha alpha dot, where lambda tilde A alpha dot equals just what I wrote. And it's an exercise for you to verify that this satisfies momentum conservation automatically. Okay. All right. So this is our canvas. Our canvas is just n 4 vectors up to rescaling for each one of them. And now we're going to have to figure out how to ask some question in this space whose answer is going to give us scattering amplitudes, and that's what we'll be turning to next. Okay, maybe I can pause again and ask if there are any questions, and this might be a good time for a short break as well. Any questions?
Nima, can you explain the notation a little bit on the right hand side, like with this A minus A plus?
Oh, I'm sorry. Yeah, sorry. Yeah, let me write it more explicitly. So, so what I mean whenever I write AB is lambda A, lambda B. Okay, and this is just the contraction of with the epsilon symbol that Mark also talked about. And actually, whenever we will also have occasion to talk about things that look like this. So this is just, so when I deal with the twistor variables, the only invariants that we can use are the epsilon symbol. And over in the rest of these lectures, every time you see something between brackets, it means that they're being contracted with the only epsilon symbol that makes sense. So in this case, this would be epsilon I j k l z a I up to z d l. Okay, and yeah, we'll be talking about that. We'll be talking about that more just in a moment when we do our crash course in projective geometry.
Okay, and all those things are A-1, A+1, and so on, is it? In the previous.
Yeah, so again, let me.
Okay, sorry.
Yeah,
I think I read it wrong.
Yeah, so this is really lambda A-1, lambda A, mu A+1 plus cyclic.
Okay, thanks.
Divided by lambda A-1 lambda. Yeah, it's a beautiful exercise, very simple, to check that this guarantees that the sum of lambda tilde equals 0. Any other questions? All right, so Song, you just want to take a little 5-minute break, and we'll come back in 5 minutes.
Sure.
Okay.
Let's come back in 5 minutes.
Okay, great.
Yeah, whenever you're ready.
Okay, great. Okay, so we've seen what our kinematic space is. Now let me just say a little bit more about the actual amplitudes in n=4 super Yang-Mills. And note that what we talked about with the momentum twistors, this is useful whenever there's an ordering and we have null momenta. And it's just a fact completely independent of dynamics that this kinematics of n null momenta is nicely invariant under these dual conformal transformations. Whether or not the actual amplitudes have the symmetry is a theory-dependent question, but just the kinematics has this dual conformal symmetry acting on it, and we've made that, and whether you like it or not, whether you knew it or not, it has the dual conformal symmetry acting on it. We've made the action of that dual conformal symmetry manifest. At the same time, finding these beautiful, completely unconstrained variables to parameterize to parameterize our n null momenta. Now I want to talk about the actual amplitudes. So as Mark reviewed in n=4 super Yang-Mills, so in n=4 super Yang-Mills, the actual amplitudes are functions of, let me write it like this. We have, and actually, I'm going to, for notational reasons later, I'm going to put a hat on these amplitudes. So this is a function of n. It's a function of this variable that Mark defined, k, that I will also define in a second. And this depends on the lambdas, the lambda tildes, and the supersymmetry is carried by these Grassmann variables. Now, Mark called them eta. I will just put a tilde on them, eta tilde. Otherwise, it doesn't make any difference. So there are 4 of these. So there's a lambda tilde, there's a lambda alpha, there's a lambda a alpha, a lambda a alpha dot, and an eta tilde ai, where I runs from 1 to 4. And that 1 to 4, the 4 is the 4 of n equals 4 SUSY. Okay, so what we're doing here, as Mark explained, is that we're actually we are deciding to label our states to diagonalize as much of the supersymmetry as we can. When we have extended supersymmetry, we have this algebra. Oops. Q alpha I, Q tilde alpha dot J upstairs equals the momentum. So on shell, this would equal lambda alpha, lambda tilde alpha dot, and a delta ij. And we'd like to diagonalize as many of the symmetries as we can. The Q and Q tilde don't commute, so we can't diagonalize both of them. But we can do the best that we can to, for example, diagonalize the Qs. Okay, so we can diagonalize Q alpha eta. I think I'm doing the other one, but anyway, let me just be a little impressionistic about this. I can diagonalize Q alpha dot I on these states eta tilde equals lambda tilde alpha dot. That takes care of the alpha dot index. Oh, sorry. So I am doing the other one. Q alpha I is lambda alpha eta tilde I on these eta tildes. So this is a Grassmann coherent state, but in practice, it's just a particular linear combination with these Grassmann variables eta tilde. That is a great bookkeeping device for all of the states in the supermultiplet, and which makes the action of the Q supersymmetry manifest, diagonalizes the action of the Q supersymmetry. So this super amplitude is a function of this n, and let me write it now in terms of this k hat, lambda, lambda tilde, and eta tilde. This has weight for k hat in the eta tildes. So the eta tildes are Grassmann variables, as Mark explained, and because I have this SU4 R symmetry that rotates these 4 indices, all the eta tildes come in groups of 4. So that component of the super amplitude that has weight comes in multiples of 4, and so that's this variable k hat. Now, for good reasons, the amplitude actually vanishes if k hat equals 0 or 1, or the sort of parity conjugate of that statement is n or n minus 1, if we have n particle scattering. In fact, one interpretation of k hat is that k hat is the number of negative helicity gluons in that component of the super amplitude. So there's a part of the super amplitude that only has gluons, and k hat counts the number of negative helicity gluons. Okay, so that's the that's our super amplitude. It's labeled by this n and this k hat, and just like we normally factor out momentum conservation, so there's a delta function for momentum conservation that we take out. It's also convenient to take out the analog for the super momentum conservation. I'm just reviewing things that Mark said. So there's a delta 4 there. There's the delta 2 times 4. This is the super partner of momentum conservation. then it's also useful to factor out this famous Park-Taylor factor from in front of everything. And that actually takes care of all the weights, the helicity weights of the super amplitude. So, so this is purely kinematics. We haven't done anything. We're just making manifest that we have momentum conservation. This is delta 4p, and this is delta 4p, and this is delta of q. Okay, so this is we're making manifest the super partner of momentum conservation. And what is left, so that's k hat, and what is left I will call m of n and k, which is still a function of lambda, m lambda tilde, and eta tilde. Nothing has changed. I've just factored these pieces out. But now I'm going to define, this is by definition, I'm going to define k is equal to k hat minus 2. Okay, and now here's the miracle, is that this m of n and k of lambda tilde and eta tilde, now we can write this as a function of the momentum twistor variables, the z, and actually a super partner, a super variable partner of the z. Okay. In other words, all the dependence on the lambda and lambda tilde and the eta tilde actually just packages into a dependence on these z's. Well, I mean, we could always do this. I just told you we just covered the sort of bosonic part, that I can solve for the lambda tilde in terms of the z's. Okay, and there's a very similar formula for the eta tildes in terms of the etas that make the super momentum conservation manifest. In fact, the formula is just the same. The tilde variables are treated the same. So eta tilde is a linear combination of the Grassmann variables for the etas. That's exactly the same as we saw before. So it's like this plus the cyclic over a minus 1a, a plus 1. Okay, so we can always write the answer in terms of the z's and the etas, but the remarkable thing is that this m and k of za and eta a is actually SL4/4 invariant. So for example, if I focus only on the ZAs, all the dependence on the ZAs, the only thing I ever see is the epsilon symbol contracting them together. Everything is invariant under SL4 transformations, and there's the extension to the super part of it. So concretely, this means that this is annihilated by generators that look like the sum over A of ZA, DD, ZA, let me just leave it ZA, DD, ZA, eta, DD, zeta, Z, DD, eta, and eta, DD, eta. Okay, so these are all the symmetries that actually that annihilate MNK. Okay, so this is the dual super conformal invariance of n equals 4 super Yang mills. Okay.
Nima?
Yeah.
There's a question in the chat about parity invariant of this amplitude in momentum twistor space.
Yes, that's right. So parity. Parity. Parity is normally lambda interchanging lambda and lambda tilde. Now, when we choose to diagonalize, let's say Q, we've made a chiral choice, right? So this is not we made lambda special rather than lambda tilde. But going back and forth between the Q and the Q tilde representation is just is like going back and forth between X and P. It's a Grassmann Fourier transform. Okay, so already even in the original super amplitude, it's a chiral on-shell superspace, and parity is a slightly interesting statement of invariance under interchanging lambda and lambda tilde, and also doing a Fourier transform, a Grassmann Fourier transform with respect to eta and eta tilde. Parity in momentum twistors is less obvious, because we've made even further choices. We've made this choice, and we've chosen to pull out the delta function for Q, and even to divide by this Park-Taylor factor. Parity is a non-trivial symmetry, and I don't know if we'll get to it, but that's one of many things that will come out of the sort of geometric description that we'll be talking about. But it is not hardwired in, and it's not even quite hardwired in the original description because of this because of the chiral choice that we've made for the superspace. I should say that it's possible to make a parity invariant choice for the superspace, but you can only do that at the expense of breaking the R symmetry. So what you can do is take the 4 Qs and the 4 Q tildes, and you can diagonalize 2 of the Qs and 2 of the Q tildes. And so you can do that to keep the symmetry between lambda and lambda tilde manifest. But if you do that, you will only see manifest in SU2 cross SU2 part of the full SU4 R symmetry. Did that answer your question? Let me see if there's another question.
Yeah.
Okay,
I guess.
great. Very good. Okay.
Sorry, there's another question. Oh, maybe I don't know if you want to answer it now. In the chat.
Okay, I didn't see it. Let me. Oh, I think I somehow closed that.
So just how do we know helicity equals 2 amplitudes until this will arise from Einstein?
We have not. Sorry, we have not been. We're not talking now about gravity amplitudes. Maybe I can come to questions, more general questions like that, in a longer just question and answer session at some point.
Yeah, sure. Great.
Okay. All right. Great. Let me go back though. I don't know. Now my screen sharing is paused. Hold on. Okay. All right. So, okay. So let's now give some examples of tree superamplitudes. And we can compute these using BCFW recursion relations, as Mark reviewed. And so here's the first famous example. So first we can talk about k equals 0, and that's just remember that was k hat equals 2, and that's the famous Park-Taylor amplitude, which in our current context, since we factored out the Park-Taylor amplitude, m and k equals 0 is just equal to 1, okay, at tree level. We'll come back to talking about loop level in a little bit. Now, next, what about m and k equals 1? Well, this is already interesting, and you can compute it using BCFW. And there are many ways of running the BCFW recursion relations, but here's one especially nice one. But if you remember, when you do BCFW, you have to make a choice of which legs to recurse on. Okay? So this is making a particular choice, but it gives the following expression: the sum over I less than j of this interesting bracket. I'll define this bracket in a moment. Now, this is what the answer turns out to be. If I had a lot longer, we could sort of talk about how we get it, but I want to emphasize the different aspects of this. Okay, so what is this bracket? Well, for any 5 momentum twistor variables or super variables, so ZA1, ZA2, up to ZA5, this is defined to be the following. It has a Grassmann delta function. So this just every time you see a delta, it just means you take a product of all these guys. Remember, it's the usual usual way of dealing with Grassmann delta functions. Here, this bracket is just the contraction of the contraction of the corresponding z's. Maybe I'll write it just the first time. I'll write it less telegraphically. ZA1 through ZA4, all contracted with the epsilon symbol times a to 5 plus cyclic. And downstairs I have ZA1 through ZA4 and the cyclic rotation, ZA2 through ZA5. And I have 5 poles until I get to the last one, ZA5. 5, 1, 2, 3, ZA3. Okay, so that's just the that's the definition. It's just so you see concretely. There's some concrete formula. Okay, and now we get it from BCFW recursion relations, but I want to talk about how we can check to see if it's right or wrong. That's one thing that I mentioned. So let's see how we're supposed to understand, for example, locality. Locality of the amplitudes. And we know, of course, intuitively, we know what locality means at tree level. It means, for instance, if I have 4 particle scattering, if I just go back to normal variables, and let's say I have these this planar ordering for fun, I can have a pole in the amplitude as s goes to 0, or I can have a pole as t goes to 0. But for example, I don't have a pole that looks like 1 over st minus rho squared. This doesn't happen. Okay, the only poles I have are simple poles when s or t goes to 0. Now, what happens, and that's simply reflecting the fact that there are in position space that we have local interactions in space-time, and the only poles occur when the particles meet, and there's a long-distance propagation of one particle intermediate state. Okay, so at higher n, if I have this ordering for the external particles, then the only poles occur in a picture like this. Okay, so maybe I have whatever's going on here, 1, 2, and then there's some I here, I plus 1, and then a j, and a j plus 1. Okay. So at tree level, the only poles we can have are when some subset of the momenta of this sort go to 0. So when I have something like pi plus dot dot, here the way I've drawn it is so let me do it like this, I minus 1. No, actually, it's fine. When I have pi plus 1 plus dot 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 plus pj squared goes to 0. Okay, so those are the only places where I can have poles and no others. Okay. Now let's see what this translates to in our twistor picture. In our twistor picture, that tells us that the only place where we can have poles is, notice that this consecutive sum of momenta, so here would be some pi plus 1 up to some pj minus 1 here, exactly these sort of consecutive sum of momenta that we're talking about, that this is going to happen precisely when these points, actually, let me do what I just is the notation that I was just using back there. These are exactly, this is the point xi, xi plus 1, and x up to xj. So the poles are exactly when xi minus xj squared goes to 0. Okay, so I have a null polygon. That's the external data. But as I move the external data around, sometimes two pairs of points can become null separated from each other. And that's the only place where at tree level, I should have any singularities in the amplitude. Okay? Now let's translate that statement in turn into what we expect in momentum twistor space. Okay, so in momentum twistor space, remember this point xi, this point xi gets mapped to the line zi plus 1. The point xj gets mapped to some zj plus 1. And so if xi minus xj squared is 0, that means that in this picture, it means that the line I plus 1 intersects j plus 1. And analytically, that means that this bracket zi plus 1, zj plus 1 goes to 0. And so again, we will review some of this projective geometry in just a moment. But I just want you to see that what it means, what locality means, is that whatever this function is, whatever this function of the z's is, the only place it can have poles are when these four brackets, I plus 1, jj plus 1 goes to 0. So that already is someone asked before how we see locality in twistor space, and here we see a more concrete version of this question. Naively, we just have this bunch of z's, and there is this ordering on them. Yes, there's an ordering on them, but naively, you could have lots of interesting, maybe even cyclically invariant functions of nz. The question of where locality comes from is that somehow these functions have to know that they care about two consecutive z's here and another two consecutive z's there, and they should only have poles when these brackets I plus 1, jj plus 1 goes to 0. Or if I say it more geometrically, despite the fact that it's a function only of the point z, somehow the functions have to learn to care when the lines I plus 1 and jj plus 1 intersect each other. Okay, so that's just the first bit of the physics of locality is where the poles are, and we can only have poles when I plus 1, jj plus 1 intersect each other. Okay, now if we go back to stare at this tree amplitude, if we go back to stare at this BCFW formula, you'll notice some funny things about this formula. So let me write down, for example, just concretely in the case of n equals 6, k equals 1. This formula tells me to look at 1, 2, 3, 4, 5 plus 1, 2, 3, 5, 6 plus 1, 3, 4, 5, 6. And so let's look at what each one of these looks like. Well, 1, 2, 3, 4, 5 is some delta 4 upstairs that I won't write down, but let's look at what the poles are. The poles look like 1, 2, 3, 4, 2, 3, 4, 5, up to 5, 1, 2, 3. And similarly, this guy has poles that look like 1 over 1, 2, 3, 5, 2, 3, 5, 6, and so on. Okay, I won't keep writing all of them down. But what I want you to notice is let's look at these these poles. Notice this pole 1, 2, 3, 4, that looks like I plus 1, JJ plus 1. Okay, that one's good. Okay, that one's a good legal allowed pole. So is this one, 2, 3, 4, 5. Looks like consecutive guys, but already the next one that I didn't write there, 3, 4, 5, 1. This does not look like a normal local pole. This is not a local pole. Okay. This incredibly simple formula, that would be hundreds and hundreds of pages of Feynman diagrams. We have this incredibly simple formula, but the incredible simplicity is coming at an interesting cost. That while for Feynman diagrams, I can imagine that each individual diagram is a sort of contribution, a local contribution to the whole answer. Here, the individual diagrams cannot actually be interpreted as local space-time processes. This individual diagram is not actually, can't be interpreted as a local space-time process. It has some poles that are correct, but some poles that are not. However, the non-local poles actually cancel in the full sum. For example, you see that this 3, 4, 5, 1 also occurs as a pole of this guy. So in this 1, 3, 4, 5, exactly the same guys make an appearance. So this non-local spurious pole occurs in more than one term, and magically the spurious poles cancel in the sum, and we're left with something that only has local poles. This was one of many early indications that these novel ways of calculating the amplitudes that were so much more efficient than Feynman diagrams, and actually more conceptually, what's interesting about BCFW is that I've just given you the answer in this way in momentum twistor space, but you see that it makes the dual conformal symmetry manifest term by term. So even though we got the BCFW recursion from the usual momenta and so on, remarkably it turns out that every term in BCFW actually manifests the dual conformal symmetry too. So it's not just simpler, shockingly simpler, but it's also manifests the hidden symmetries. Okay, so that's some actually early indication that we derived BCFW thinking about what the poles look like and shifts and so on in the ordinary momentum space. It turns out that it also manifests the dual conformal symmetry, again, term by term. But therefore, that's why term by term, it doesn't really care about locality in space-time. It doesn't care about locality in the original space-time. It doesn't care about locality in the dual space-time. It's about something else. And one of the things that we'll be understanding is what that something else is. So, okay. But that's one of the features, is that term by term, it doesn't look like a local space-time process. Each individual piece doesn't look like that, but the building blocks are these remarkable objects that manifest all the symmetries of the theory. And on top of that, they have to be put together and glued together in a particular way to get the final answer. In fact, there are many ways of doing BCFW. There are many, many ways of doing BCFW. They all give you different formulas. So that's one funny feature here, is that the answer should be completely cyclically invariant. The super amplitudes are cyclically invariant. They should have this cyclic symmetry. But the fact that the recursion forces you to make a choice is seen in this formula. It breaks the cyclic symmetry manifestly. This index 1, for example, is special. Okay, I chose particle 1 to be special. So, for instance, there has to be some identity that this is equal to the same thing if I replace 1 with 2. Okay, and so this is a non-trivial identity. Okay, so this is a non-trivial identity. And so these are sort of many indications that that these objects, are coming from somewhere else. That they make all the symmetries manifest. They don't make locality manifest. You can use them to build the amplitude, and they have to satisfy lots of magical relations between each other in order for this all to be possible. But a picture gradually started emerging that you should somehow think about the different terms in BCFW as triangulating something, as pieces that sort of fit together in order to cover the inside of some kind of abstract geometric region. And we'll see more of how this. We'll be seeing, of course, how this works in very concretely in a bit. But just to give the sort of rough idea is that different ways of doing BCFW correspond to different triangulations of exactly the same object. And there might be totally different ways of triangulating. In fact, there are totally different ways of triangulating that don't even look anything like BCFW. But the fact that it's what I wanted you to take away from this is that first, what locality means is this very simple thing about where the poles are, at least at tree level. The poles are when these four brackets I plus 1, JJ plus 1 goes 0, when the corresponding lines intersect. Second, that these beautiful ways of recursively calculating the amplitudes are representing them in a very new way, where locality in either the original space-time, locality and unitarity in either the initial space-time or the dual space-time are not manifest, but all the symmetries are manifest. There's no unique way of writing them down. There's no canonical way of writing these formulas down. Unlike Feynman diagrams, so there's a canonical way. Just sum over all the diagrams. Here, there's no one way of writing down the answer, and these are all clues that we should think of the answer as actually breaking up some sort of master geometric object into simpler building blocks, and that's exactly what we'll be seeing in more detail. I should have actually said this much earlier, but this dual conformal symmetry, and perhaps Mark said this. But the dual conformal symmetry is actually interpreted as the fact that this M and K of the Zs is actually the expectation value of a Wilson loop. So, you know, in the same theory, in n equals 4 super Yang-Mills, so we have this null polygon in the dual space. Even if I work with the x's, I have a null polygon in the dual space, and so a natural thing that you do whenever you have any closed loop is to think about the expectation value of the corresponding Wilson loop. So the expectation value of this null polygon in this dual space-time is the physical interpretation of this MNK object, and it's actually the supersymmetrization of that is really most naturally done thinking in terms of these supersymmetric Wilson loop variables, these supersymmetric momentum twistor variables. But anyway, there's a certain supersymmetric Wilson loop calculation associated with this null polygon. And so we have one object that we think about in ordinary space-time as a scattering amplitude. When we strip off momentum conservation, we make that manifest by drawing this null polygon. And in this dual space-time, and stripping off momentum conservation of the Park-Taylor factor from the amplitude, what we're left with is a Wilson loop or a supersymmetric Wilson loop in the dual space. So it's interesting that there is a local description of the physics, a standard local description of the physics on both sides. We have n equals 4 super Yang-Mills on both sides. On one side, we calculate a scattering amplitude. On the other side, we calculate a Wilson loop. The conformal symmetry is made manifest in locality in the original space-time by the scattering amplitude. The locality in space-time and the dual conformal symmetry is made manifest by the Wilson loop. But neither one of these Lagrangian path integral pictures make all the symmetries manifest. They don't make the other side obvious. That is, as Mark mentioned, the conformal and the dual conformal symmetry are joined into this infinite dimensional Yangian symmetry. So So we have this infinite symmetry that the amplitudes have, and the Lagrangian description doesn't make this obvious at all. So you can make one small part of it obvious for the conformal symmetry, another small part obvious for the dual conformal symmetry, but not both. And yet, what we see from these recursive ways of doing the calculation, just to repeat, is the building blocks have all the symmetries in them, all the Yangian symmetries in them, but they don't care about either the original space-time or the dual space-time. They make the shocking simplicity of the answer manifest, but how you have to combine all the building blocks together is still something which we derive from quantum field theory. We derive from the desire to get the right answer that's local and unitary. But what we'd like to do is see these emerge as the answer to a different question, which will make all the symmetries manifest and explain where locality and unitarity actually come from. So we really want to, at least in this context, we want to reverse the question and find a new object, a new sort of question in this kinematic space to which formulas like the one that I just wrote above are thought of as the answer, and one particular triangulation, one particular way of representing, breaking up a geometric object into a piece. Okay, now let me make one more comment about how we're going to think about loops. Okay, so now at tree level, just to say, at tree level, the amplitudes only have poles. They're rational functions and they only have poles. At loop level, the amplitudes are much more complicated. The actual amplitudes are much more complicated. They have logarithms, dilogarithms, and all the more complicated functions that you've heard of from Claude's talks. The state of the art is that we understand what functions make an appearance, what kind of functions make an appearance for any field theory at one loop. So we understand that perfectly. In 4 dimensions, they're up to certain dilogarithms, and we know exactly which ones they are. Anyway, and there's an analogous statement at any number of loops, and the sort of frontier of what we understand about these things today is 2 loops. Okay, so a lot is understood about 2 loops, not everything, and people are working to try and understand more about it. The conceptual difficulty, and this is where the sort of S-matrix program of the 1960s really hit a roadblock, is that we don't know ahead of time, if you just hand me the amplitude, the final amplitude, non-perturbative if you like, or maybe even in perturbation theory, we don't know how to check what properties of this function guarantee the sensible physics that we want. And the sensible physics we want is sort of causal, local, and unitary evolution. Now, unitarity is easy enough to check. You just check if S dagger S equals 1. Lorentz invariance is easy enough to check. You just check if things are functions of Mandelstam invariance or whatever. But causality is the difficult one. And the reason is sort of physically obvious. Again, we're just throwing things in from infinity. They come back out to infinity. And we want to see what is the fingerprint in these functions of the fact that somehow what happened inside could be given a causal time evolution interpretation. Now, we've known for a long time that causality at the level of amplitudes is reflected somehow in the analytic structure of the amplitudes. The fact that the amplitudes are not random crappy functions, but they have decent analytic continuations in the complex plane. But that's not everything. I mean, it's they do, after all, have a very intricate structure of branch cuts, so they're not perfectly analytic everywhere. And so we don't know precisely how the branch cut structure, what the branch cut structure should be a priori in order to be compatible with causal evolution. That's what the people in the 1960s thought that they could figure out. They thought they could responsibly derive from the top down what the analytic properties of amplitudes should be in order to reflect causality. And there's many reasons why that was doomed to fail. Many good reasons why it was doomed to fail. Not the least, which is that on very general grounds, it's very easy to see that it's impossible for all of the singularities of the amplitudes to actually correspond with what you're trying to analytically continue in the complex plane, right? Well, if you analytically continue in the complex plane, you want to understand all the singularities everywhere. Your rough pictures of the singularities are associated with particle production and can be controlled by unitarity. But for that to be the case, all of the singularities should occur for Lorentzian momenta. And it's easy to see that's actually impossible. There's zillions of singularities that are not associated with anything that has an interpretation in Lorentzian momentum. Those are things that back in the day were called anomalous thresholds. But anyway, they're ubiquitous, and you wouldn't have expected them to. In fact, it would be a kind of a shocking thing if it was true, and it's not true. So this is one of many indications that if you're going to think about this, you have to invert the problem. And that's the sense in which the attitude we're taking towards this physics is the opposite of the S-matrix program. We're not trying to derive the result, the meaning of causality in the analytic structure in some very responsible way. We have to go backwards. We have to make a guess of some structure, something new. We have to look for some new principles, new laws, new ideas that spit out these answers, and that we can then read out from them what this analytic property has to be, so we can interpret the object that we're talking about as the amplitude. So I'm going over all this just to highlight again what the essential novelty is. That unlike seemingly, I think it's a big irony that here in the year 2020 we know so much about Euclidean conformal field theory, and we can do all these amazing things, non-perturbative things with the bootstrap, all this fantastic stuff. And yet we still don't know the answer in QED, something that actually describes the world we see outside our window. We don't know what the rules are for how to decide whether an amplitude is good or bad. And the essential novelty is time. Once again, the essential novelty has to do with the fact all these branch cuts, all this complicated analytic structure is reflecting the physics of time evolution. And we cannot retreat to Euclidean space to get the right answer. Okay, so that's the big advantage we have in thinking about the quantum field theory in the usual way, is in Euclidean space, everything is perfectly sharp, especially in conformal field theories, it's 100% sharp. But we don't have that luxury when we're talking about these on-shell processes that involve particle scattering. So all of this is to say that that we don't ahead of time know what the rules are that govern amplitudes, even in perturbation theory. Never mind non-perturbatively. But the situation is better or easier if we just back up one step to getting the full amplitude. Okay, so and for that I need to talk about the notion of the integrand of the amplitude. So what do I mean by the integrand? Oops. Sorry, guys. Don't know what happened there. Oops. Okay. Well, let's think about let's think about something something simple. So imagine that we have this one loop diagram. So what do I mean by the integrand? Well, it's what we normally do when we first take field theory. When we sum up all the Feynman diagrams, but we leave the loop integrals for later. Okay, so so here for this simple box diagram, for example, we would have something like this, right? So we'd have d4l 1 over l squared, l plus p1 squared, L plus P1 plus P2 squared, L minus P4 squared, okay? So in this case, the integrand, at least for this diagram, would just be this form, if you like, D4L over all the four propagators, okay? Now, this is a simple rational function, okay? So it's doing the integrals that gives me all these interesting transcendental functions, but this part of the integrand is clearly a rational function, okay? Now, an important point is that there is actually a notion of the integrand, and this notion makes sense in planar theories. And actually, it also makes sense beyond the planar limit, as we'll talk more about tomorrow, so long as you think about it in the genus expansion. But let me just stick with talking about the planar limit for now. Now, what do I mean by this? Well, you might say, well, obviously the integrand makes sense no matter what, right? But it's not so obvious. Like let's say we take two. Let me just to begin with. Let's take a couple of different kinds of diagram. Okay. I don't know. So here's one diagram, and one two-loop diagram, and I don't know. Here's another two-loop diagram for the same number of legs, something like that. Okay? So what is the problem? The problem is that you know, here I want to say, oh, here's L1, you know, and then maybe here's some L2. And so here I'd write down D4L1, D4L2 over a bunch of propagators. The problem is here on the second diagram, I also need to put some L1 and L2. But if I want to be able to talk about adding the diagrams together, I have to somehow identify what I mean by L1 and L2 in the second diagram relative to what they are in the first diagram. And a priori, if you have a random diagram, it's not obvious what you mean by the loop momenta in this diagram versus what you mean by the loop momenta in another one. That's why it's not obvious ahead of time that we can, in fact, combine everything together to one master integrand. But we can. In the planar limit, we can. And in order to make sort of manifest how we do it, it's actually useful to go back and even think about this loop diagram in our language of these null polygons. Okay, so let's say we go back to this simple example. Then let's draw our null polygon already here. So particle 1. So we draw this sort of square for the null polygon, right? So this would be let's say my point x2, x1, x3, and x4. Okay, so that this momentum P1, this would be P1, and that's that null line, and so on. Okay, all right. But you see, what does this look like? This null polygon looks like we're starting to draw a dual of this diagram. What we've done in every face here, on this face out here, I've put a point in the middle. On this face here, a point in the middle, and so on. Okay? So it's natural to put the point in the middle of the actual face of the loop. And so let me call this point x0. And now you see something very nice happens. If this loop was L, that L is also, L mu is nothing other than x0 mu minus x1 mu. Okay, and therefore, this form that I'm integrating, D4L over L squared, L plus P1 squared, dot, dot, L minus P4 squared, this is more elegantly written in terms of the x's. It's D4 x0 over x0 minus x1 squared up to x0 minus x4 squared. Okay, so we can think about loop variables as just being points in this dual space in which the null polygon lives. And you see in the second form, the symmetry is, I didn't even have to choose who is L, right? Here I made a random choice to put L on this leg versus on that leg and so on, but it's more uniform and more symmetrically represented in the dual language. Okay. Okay. So that means that we can think about trade loop variables for points in the dual spacetime. And because of that, if I draw all the diagrams on, if I take two diagrams again, so let me take I don't know, let me take this example plus maybe I'll just do it the other way around. Okay, so let's say I have these two diagrams. Then I know how to add them together. I simply put an x here and a y, and here again I have x1, x2, x3, x4, and x5. And so, and also there's an x here and a y there, and x2, x3, x4, x5, x1. So over here, I would write down the form d4x, d4y over, and then I have that line. Every one of the loops is just associated. I mean, I draw the sort of dual of the diagrams. I would draw it like this. So here I'd have x minus x1 squared, x minus x2 squared, x minus x3 squared, and then y minus x4 squared, y minus x5 squared, y minus x1 squared, and also even this intermediate loop is x minus y squared. Okay, so that's what I get from this guy, and I can do exactly the same thing for that guy, and it makes sense to add them together. Now, in fact, there's only one more thing that you have to do. There was an ambiguity in which loop I put the x and the y in, so you simply symmetrize. Okay, so the answer that you get is a form which at L loops has L is a function of L points in this dual space-time, and you symmetrize. You symmetrize over all L of these loop variables. But when you do that, it canonically makes sense to add all the diagrams together under one master object that we can think of as the integrand. So the notion of the integrand makes sense in the planar limit. And as I said, also in general, when we think about drawing refinement diagrams on surfaces and looking at their dual diagrams, which we'll be talking about more tomorrow. But here today, we're just talking about the planar limit for n equals 4. So that means that that there is an object that we can talk about that's just a rational function. Well, really, it's a form. If we have L loops, it's a 4 times L form, and so we don't have to deal, at least immediately, with all the complexities of the complicated transcendental functions. We can sort of at least approach part of the problem by trying to determine what this integrand looks like. Okay, now let me say let's now translate this in our language of our kinematic space. So let's go back and talk about this. The simple box example. So here I have some x naught. So how are we supposed to think about x naught in twistor space? Well, x naught is just going to be some line in twistor space. Okay, so this loop variable is going to be a line, and I'm going to be using this notation a lot for the loop variables to remind myself that it's a line. So this is in the dual space-time, this is in twistor space. I'm going to label the line by 2 points on it, A and B. Okay, so my loop variables will be a line, will be AB sub I for I equals 1 to L. If we have L loops. And now let's translate what this box looks like in momentum twistor space. I'll actually leave you the exercise to sort of like literally derive it, but let's see. But we can sort of easily see what it can be. So first, whatever we're doing, we have some kind of foreform. So, but on the other hand, we have this ZA and ZB. But we have ZA and ZB up to this 2x2 linear transformation. I can move A and B around on this line. So up to exactly this 2x2 linear transformation that we talked about. So I will call this. So this is an action of a GL2. Okay. So so I can think of it as D4ZA, D4ZB. Well, that's naively 8-dimensional, but I have to mod out by the action of this GL2. So that takes me to that takes me to a foreform. And so actually, let me just, I'm going to use a condensed notation here, and we'll talk about this more. We'll talk about this in a little bit of detail. But D4ZA, D4ZB mod GL2, I will just write as D4AB. Okay. Now, so much for the loop part. Now let's look at this propagator. So this x0 minus x1 squared, x0 minus x1 squared. Now, I perhaps should have said this when we first talked about this correspondence. Actually, let me not say this in detail now. I'll say it a little more when we do our crash course in projective geometry in a second. But certainly, x0 minus x1 squared goes to 0 means that AB means that AB12 goes to 0, right? Because this means that the line AB and the line 1, 2, which corresponds to that point x1, intersect each other. So AB12 goes to 0. So that means that all the poles just look like these poles in the momentum twistor variables with these 4 brackets, AB12, 2, 3, and so on. So this diagram in momentum twistor space would be D4AB over AB12, AB23, AB34, AB41. And if you remember, everything that we do has to be invariant when we rescale all the twistor, independently rescale every twistor variable by itself. So we should have a rescaling ZA goes to TA ZA. But downstairs, the 1 occurs twice, 2 occurs twice, everyone occurs twice. So actually I have to multiply this by 1, 2, 3, 4. It doesn't depend on AB, but 1, 2, 3, 4 squared. And now this has all the correct weights. You see that there are 4 ABs upstairs and 4 ABs downstairs. So that's invariant under the rescalings. It's GL2 invariant, and it's invariant under all of these rescalings. Okay, so what we think of as the loop integrand, therefore, is are functions of these lines in momentum twistor space, and the loop integration is a form in the is this 4 times L form that we're looking for in the momentum twistor space. Okay, so now that we're talking about the integrand, so we can summarize, talk about the kinematical space for the integrand. So we still have our Zs. We have Z1 through Zn. And these guys have an ordering, as we talked about, a cyclic ordering. So we group them into a 4×n matrix. Geometrically, there are a bunch of points in P3. But also, we have, in addition to this, we have a bunch of lines, AB1 up to AB sub L. So we have N points and L lines. Okay, so in the space we have, there's one line, there's another line, there's another line. We have these lines, AB sub I, AB sub I. Okay, so that's it. That is our canvas. Okay, so so again, what is our this is the way we're now talking about the data labeling the amplitude. Now we're cheating a little compared to what we really should be doing, because we're not talking about the full amplitude. We're not talking about the, if you like, the integrated amplitude. We're talking about the integrand for the amplitude. So we still have some information in this kinematic space which is gone in the end. We integrate over the loop variables in the end. Now we're talking about the integrand, but once we talk about the integrand, this is what it depends on: n points with an ordering and L lines, and that's it. That's all we have. That's our space. Once again, there's no metric, there's no locality, there's no time, blah, blah, blah. Just to say one more time, our challenge now in this space, and this is the whole thing. Now there's nothing more to say. In this space of n points and L lines, we have to find some structure, some question that's going to spit out as an answer amplitude. Okay? Just to give you an example, just so we complete this survey, here's an example of the sort of simplest non-trivial loop integrand. Example loop integrand. So mirroring what we did, where we wrote down that simplest k equals 1 tree amplitude. Now I want to give you the simplest loop integrand is actually for k equals 0. So it's for k equals 0 or the MHV amplitudes. And so, and this is what it is at one loop. So the amplitude or the integrand at one loop depends on the z's. It depends on a single AB, and is the following expression. It looks kind of rather similar to the one that we wrote before, but with a slightly different object I'm now going to define. Okay. Where this object now because it's k equals 0, there are no etas. Okay, we have no etas here at all. Okay, there's no helicity dependence. All of that has gone away. So what do we actually have? So it only depends on these bosonic z's and this line AB. Okay, and so this object, this 1 I plus 1 JJ plus 1 is it's a form, so it's got the D4AB, but it has an interesting numerator: A1 II plus 1 B 1 JJ plus 1 minus A swapped with B all squared divided by AB II plus 1 AB 1I AB 1I plus 1, and then the same thing with J's. AB JJ plus 1 AB 1J AB 1J plus 1. Oh, and I should say that this is what you get from a loop level extension of BCFW. So for n equals 4 super Yang-Mills, there's an extension. It involves a number of extra ideas, but there's an extension of the BCFW recursion relations that lets you get the integrand to all loop order. Okay, so at least in principle, recursively get it to a loop order. But again, it's especially simple for these simple examples. So that's it. That's what you get for the one loop. That's what you get for the one loop integrand. And once again, just as in our previous example, let's see what locality and unitarity mean for this guy. Okay, so what does locality mean for the loop amplitudes? Well, locality at loop level, what kind of singularities can we have? Well, let's say at one loop, we can still have singularities where you have something, you know, maybe where you have now a one loop on one side, but still an intermediate virtual particle that goes on shell. Okay, so these singularities are the same as the ones that we had before. So these are still going to be when pi plus dot dot plus pj squared goes to 0, or when I plus 1, jj plus 1 goes to 0. But we can have a new kind of singularity where this internal loop momentum can go on shell. So this internal loop momentum can become null and go on shell. And when that happens, intuitively, what you should get is what's called a single cut. It's like, since this particle is on shell, it's as if you have a tree amplitude with these two particles having equal and opposite momentum, and everything else the same as before. So this is some L and some minus L with L squared equals 0. So we should have a singularity when L goes to 0. And the singularity should be interpreted as a one lower loop, in this case, a tree amplitude. Okay, but to begin with, where the pole is, the pole has to be when x minus xi squared goes to 0, or when ab I plus 1 goes to 0. Okay, so those are the only poles that we're allowed to have. So if I summarize what locality says, is that the poles of the integrand should be when I plus 1, jj plus 1 goes to 0, when any given loop AB sub alpha, I plus 1 goes to 0, and finally, two loops can become an internal loop line. Can I could have something like, I could have a situation where this internal loop goes on shell. Instead of being virtual, it goes on shell. So I can have poles corresponding to those guys, and that's when these internal guys go to 0. So that's where the poles can be. That's locality. As we'll talk about more, unitarity is a particular kind of factorization. Oops, sorry. I don't know what's going wrong with my pen here. So unitarity is a particular kind of factorization to lower point and lower loop amplitudes, which we'll talk about in a little bit more detail. So these are the properties that whatever this theory that we're looking for in this kinematic space has got to give us. But let's go back again to our example, to this formula, much like our previous example. So it's an extremely simple formula instead of thousands of Feynman diagrams, thousands of terms, and well, even thousands of Feynman diagrams. We go to large n. I mean, this expression is true for any number of particles. So it's incredibly simple. But you see that there is a legal local pole. Here is a legal local pole. But every one of these terms has 4 illegal poles in it. So these are not in general local poles. One I plus 1, and so on. Okay? And yet, once again, just like before, they have to be grouped up and add up in such a way that that we get a local answer with only local poles, and that factorizes correctly to give us unitarity. Okay, all right, so let me pause here and ask if there are any questions. Okay, so, all right. right. So now, so I've set things up. So I hope you now have a clear idea of what this kinematic space is, and what our question is, what the challenge is. Now I want to give you. I'm going to jump to the end and just tell you what the answer is. Okay, just and it's going to look a little strange and abstract at first, but I just want you to see. This is something I can easily do in the 20 minutes. I want you to see what the character of the answer looks like. But well, let me give you again a sort of a rough idea. A rough idea first is that so we want to know what is the question. So what is the question in kinematic space whose answer is the super amplitude? What is the question in kinematic space whose answer is the super amplitude? And this is the, let me just sort of first say what the qualitative idea is. So here's our kinematic space. Okay, so this is just, imagine this is again our canvas. This is our kinematic space. What is the kinematic space? It's the space of our n, z's, and the AB1 through ABL. So if I have a kinematic space at L loops, that's it. I have this kinematic space. And the idea is that we're going to identify in this kinematic space, we're going to naturally see a certain geometric shape. I'll talk about more precisely in a second about what the shape is and how we see it. But there's going to be a certain geometric shape that naturally lives in this kinematic space. And this shape is going to be called, generally speaking, these shapes are called positive geometries. And the reason for the word positive and so on will make sense in a bit. These are, but you should think of them as generalizations of the interior of a triangle or the interior of polyhedra, higher dimensional polytopes, and curvier generalizations of them that we will talk about. But that's sort of roughly what you should keep in mind. The important feature of these geometries is that they have boundaries of all dimensions. So if you have a triangle, there's the interior, it has edges and it has points, and higher dimensional polyhedra and polytopes have the same property. Well, that's the most important zeroth order fact about these geometric regions. So in kinematic space, ultimately, we're going to be identifying some positive geometry. This is a purely geometric statement. And associated with these positive geometries, associated with them are certain canonical differential forms. And I'll be defining all of this precisely, but this is a certain differential form that is fully determined by having singularities, prescribed singularities, the so-called logarithmic, which I'll just define later, but there's certain prescribed singularities, logarithmic singularities, on and only on all the boundaries of this positive geometry P. Okay, so there's some sort of all right. So there's a geometric part of kinematic space, and associated with that is a certain differential form that's completely determined by it, by the requirement of having singularities on and only on all those boundaries. And that differential form ends up directly being the super amplitude. Okay. So this canonical form omega will end up being literally the super amplitude. And let me make a I'll make a little digression to explain how this works. Everything in all of these words that we're just talking about in this kinematic space, nowhere did I tell you about where the super etas went. So the helicity information and the supersymmetric information went in those Grassmann variables. Where is that Grassmann stuff? Well, it's not there. It's traded for something. It's traded for something else. So there's a Bosanic way of thinking of the SUSY. And it's extremely simple. Let's say we have this super amplitude that's a function of the ZA. So the ZA have their index, and we have the etas that also have 4 indices. Now, let me call them capital A, just so I don't confuse the two. Okay, so so I runs from 1 to 4, and eta runs from 1 to 4. Okay, so and remember the etas are anti-commuting. All right, but in fact, we can trivially construct from this a differential form instead. So this was m of n and k, and this had weight for k in the etas. Okay, that's what we got, 4 times k. So instead of that super amplitude, we're going to talk about a 4 times k differential form that only lives on the ZA. And how do we get it? Well, it's obvious. We take each one of these eta I, and we just simply replace it with a dz. Okay? Now, that's good. The etas are anti-commuting. Differential forms are anti-commuting. So this is a trivial way of thinking about the supersymmetry in a bosonic way. There is something interesting about it, though. It's not a priori obvious that this is a good idea because of exactly what I emphasized. There's a separate SL4 symmetry acting on the Zs. That's the bosonic conformal or dual conformal symmetry. There's a separate SU4 that acts on this R symmetry index. Now it's completely unambiguous. I'm free to identify the two if I want, and I'm free to make this identification. Certainly, if I do this, I can go back and forth. If I give you an expression with the dz's, I can go back and forth and get you the expression in terms of the the etas. But this is an interesting differential form, which has the property that the dz's in this differential form only ever contract with themselves, and the z's only ever contract with themselves, so that despite the fact that naively, I only have an SL4 symmetry associated with this form, it turns out to have this SL4 cross SL4. It turns out to have 2 different symmetries. Okay? So instead of talking about a super amplitude, I talk about a differential form on the kinematic space. And in fact, this is a quite general idea. It has nothing to do with supersymmetry. If we go back even to ordinary lambdas and lambda tildes, we normally say that we have these different helicity amplitudes, let's say, and that if I have this helicity amplitude, it's a function of the lambdas and the lambda tildes, and I have a different one as a function of the lambdas and the lambda tildes, that it doesn't make any sense to add these together because they have different weights under rescaling. The amplitude has a weight under rescaling lambda and lambda tilde. Oppositely, the amplitudes go like TA to the -2HA times M, so it doesn't make any sense to add the amplitudes together. fact, the only way we know of to add the amplitudes together is to introduce polarization vectors and sum them all into the Feynman non-amplitude. So we can sum all the Feynman diagrams with polarization vectors, and only when we dot with the polarization vectors we get the actual amplitude. The actual the thing before we dot into polarization vectors is what we normally compute with the Feynman diagrams. But directly on shell, we normally think there's no way to add different amplitudes together, unless you have something like supersymmetry that gives you a good reason to put them in a multiplet. So then we can organize them together, introduce these Grassmann variables, organize them together, and put them all into the function of these Grassmann variables. But I can do something else. I can take, for example, any negative helicity amplitude, okay, even in the standard model for gluons, for photons. And if this is for particle A, and it's negative helicity particle A, what I can do is wedge it into d squared lambda tilde for A. And now this thing, is neutral under the little group scaling, so it makes sense to add them together. And I can do the same thing with a positive helicity amplitude. So this is a function of lambda and lambda tilde, lambda and lambda tilde. Okay, but the helicity weights cancel when I wedge into these d squared lambda tilde and the d squared lambdas. So we could really think about the amplitudes in the standard model is this, let's say for the massless particles in the standard model, just for fun, I can think about those amplitudes as forms on lambda and lambda tilde space. Okay, there are certain differential forms on lambda and lambda tilde space. This idea is not special to a supersymmetry at all, but it's especially useful and interesting in the supersymmetric context. And what we're doing, going back to our momentum twistor space, just to say it again, we can think of, instead of the super amplitude m and k of z and eta, we can trade it for a 4 times k form just on z space. Okay, and if I'm talking about the integrand, then I would have an m and k of z and eta, and I have a bunch of ab's, which beforehand I was already wedging. There was already a form on this part just from wedging all the loop variables. So this gets traded now for a 4k plus 4l form on z and z space and AB. Okay, so once again, now starting to fill the picture in a little more. Here's our kinematical space, whatever it is, it's space of the space of the nz's and the AB1 up to ABL. And the claim is that now in this space, we're going to find a positive geometry, P, and the super amplitude will be omega 4k plus L is a form on this Z space and AB space with logarithmic singularities on P. Okay, so that's what the actual integrand for the super amplitude, integrand for super amplitude is going to be thought of as this canonical form with logarithmic singularities on the boundary of this positive geometry. And in the context of n equals 4 superioring mills, this positive geometry is the amplituhedron, or in fact, it's the kinematic space description of the amplituhedron. The initial way that these objects were talked about was in some auxiliary space, but a few years ago, we understood how to think about them directly in kinematic space. And it's really this direct description in kinematic space that allows one to start thinking about these ideas more generally, and especially in the context of the theories that I'll talk about tomorrow, the scalar field theories with no SUSY and so on. And also in other settings, you can start looking for geometric structures in kinematic space anywhere you encounter such kinematic spaces. For example, also even for questions involving cosmological correlation functions and other things too. Okay, so that's the rough sort of thing that we're looking for. And now I just want, in the last few minutes here, I just want to just tell you exactly what it is. Okay, so it's going to look, it might look slightly abstract at first, but I just want to emphasize that we can summarize it all on this page. Okay, so in order to do this, I'm now going to be a little more specific. You can say, well, where does this geometry come from? I just have the space of Z. Where does it come from? Well, we're going to be seeing where it comes from. So in this kinematic space of the Zs and the ABs, we're going to first find what you can think of as a sort of top dimension. So this is a high dimensional space. Actually, what is the dimensionality of this space? The dimensionality of this space is, you know, every Z, there's 4 Zs. So we have, it's a 4-dimensional vector. So we have 4 n variables for the Zs, and each one of the ABs also has 4 variables associated with it, just 4 loop variables. So it's a 4n plus L dimensional space. Okay, this is our kinematic space. It's 4 times n plus L dimensional. We're looking for a much lower form. It's a 4 times k plus L dimensional form. Okay, so this is going to be a form that's low dimensional, living in this big space. Okay, so the first part of this, the first part of the description in the kinematic space is that there is going to be a region in this kinematic space, a kind of good region. You can call it a positive region. It's not yet the positive geometry, but it's a positive region in this kinematic space. And this positive region is going to end up is determined by purely topological notions. Again, we'll talk about what it is in more detail later, but just so you see that I can summarize what it is concretely. And I'm going to write down what the minimal description of this space is. There's a nicer, more symmetric description. But from it you can derive this very minimal one. So here's the minimal one. This positive region P is defined simply by the requirements that all of the, in fact, since you're not going to understand this in detail anyway, let me give the more invariant definition. This is defined by requiring that if I take any 2 consecutive B's, so I fix B and I fix A, and so I fix B and A, and then I scan over all the rest of the Z's. Okay, so I get it. So I fix B and A, and I look at the sequence. I look at this sequence of 4 brackets: ZB, ZB plus 1, ZA, and then I scan over all the ZI equals 1, 2, blah blah, n, skipping B and A. Okay, I skip B and A because if I equals B or I equals A, this bracket is equal to 0. I'm antisymmetrically contracting something with itself. Okay, so this gives me a sequence of numbers. Okay, I get a sequence of numbers, and I demand that the sequence of numbers has k sign flips. Okay, so might seem absolutely bizarre. We're now starting to talk about positivity, negativity, sign flips. This turns out to be quite simply a topological condition, kind of a winding number condition on how this configuration of Z's winds. There's the Z's are points in P3, and there's a three-dimensional notion of winding number. But this is what captures this three-dimensional notion of winding. It's this very simple statement about a certain sequence of these four brackets having a prescribed number of sign flips. So that's part of it. Then I have to tell you about the ABs. So similarly, if I take any one of the ABs and I fix any A, and I look at the sequence, I take the bracket with the AB alpha and a ZA, and again, a ZI equals 1 through N, skipping A. This has K plus 2 sign flips. And these funny numbers, K and K plus 2, actually end up being extremal. They're the maximal number of sign flips that you can have. So there isn't really, they're not randomly chosen. But anyway, I'm just telling you what the answer ends up being. And also that all of the AB alpha, AB beta, all these brackets, that the lines shouldn't intersect each other, and we're going to enforce that by just asking that all these brackets are positive. So if you like, all of these have 0 sign flips, so they're all just positive. Okay. All right. So that is a certain positive part of this big configuration space. But we're interested in this form, this omega, which is a 4 times K plus L form, which is a lower form in this big positive space. So I'm also going to define a certain family of subspaces. I'm going to have a 4 times. I'm going to have some 4K dimensional. I'm going to have a 4K dimensional subspace in this whole space, 4K plus L dimensional subspace in this whole space. Now let me define what that subspace is. The L part is just simple. It's just all the ABs. So there's no subspace involved there. So what I'm going to do is define what this, some part of the Z space. So I'm going to define a 4K dimensional a 4K dimensional subspace in this 4N dimensional space of all the Z's. And what is a subspace? Well, it's the simplest possible thing. It's the simplest thing I can do. My subspace, 4K subspace of Z space is, it is just a linear subspace in Z space. In other words, it's all the Z's that I get by starting from some particular Z, any particular Z that I like, and I translate in 4K directions. So I translate, here's a variable y alpha I. So these deltas are fixed. I runs from 1 to 4. This alpha runs from 1 to k, and so geometrically, this is like I take some particular point in Z space, Z star to begin with, and I just translate it in the direction of a particular k plane in n dimensions, which is parameterized by these deltas. Okay, so in other words, this is a family of subspaces. It's a family of subspaces that's labeled by the subspace S 4K is labeled by this data of the initial choice Z star of this initial point and this delta alpha A. So this groups into a 4 plus k by n matrix of the z's here, of the z star and the delta. Okay, so that's a subspace, and there's a certain positivity condition on the subspace that I will talk about later. So this has to be this matrix has got to be positive, and I will define what that means later. It's a very simple requirement. But anyway, that's it. So we have this. We have our kinematic space. We have a positive region of the kinematic space that's purely defined topologically, and can be characterized in terms of these interesting sequence of Steinschler patterns that are the simplest invariant characterization of a certain pattern of winding for these z's. There's a 4K dimensional, 4K plus L dimensional, but the interesting part is the 4K dimensional subspace that's just a linear affine subspace in this whole space. And now the claim is that the intersection of this subspace S, this family of subspaces S, with this positive region actually is a positive geometry. Okay? This intersection is the kinematic space amplituhedron. And the super amplitude is the unique locked differential form with the property that when you pull it back to this subspace, now we found a subspace of the correct dimension. So it makes sense to take omega and pull it back to this subspace. Literally just evaluate it on the subspace. And omega is completely determined by the demand that when it goes on the subspace, it gives you it yields the canonical form with logarithmic singularities on and only on the boundaries of this kinematic space amplituhedron. Okay, now almost none of that probably makes any sense to you right now, but I just want to make two comments about it. One, this is the entire description. Okay? I've not left anything out. This is and we said from the beginning that it's not obvious what to do in kinematic space. All we have are these z's. We have these z's, maybe we have these extra lines when we go at loop level. So that was our question. We don't have a Lagrangian, we don't have locality, time, evolution, none of the things that we're used to. So something new had to happen. And the beginning of everything is just this little idea of the ordering. You see, the ordering on the outside begins to make it possible to talk about things like winding and topological notions and things like that. We'll see it in more detail. But just that frisson of structure with the ordering on the Z is enough to let you get started. And it looks strange and it looks unusual, but it had to look strange and unusual because we have to have something that replaces time evolution, causal evolution, locality, unitarity. All of those things are an output. And we can actually understand quite simply why the poles of this form only occur in the correct spots. When II plus 1, JJ plus 1 goes to 0, why when you go on the poles, you have factorization to lower objects of the same form. All of these facts that encode locality and unitarity are actually a consequence of this positive geometric structure in kinematic space. Okay, so that's all I'll say about this for now. I just wanted to jump to the end here so you had some idea of the kind of beast that we're going to be dealing with. I guess this is a good time to stop, and when we come back, I will go back to a basics, and we'll talk. We'll do some sort of crash course in projective geometry, and tell you about some of the very basic things that you need to know to kind of play with these ideas. All right, so maybe I'll stop it there and take questions.
Okay, so there's a question in the chat. Is the fixed delta optional?
No, in fact, it's not fixed. You can choose any delta that you like. There's just one positivity condition. The matrix of Z and delta has to be positive in a way that I'll explain what that means. In fact, it's a very simple condition. Given any k by n matrix, you say it's positive if all the minors of the matrix are positive. All the maximal minors, all the k by k minors are positive. We'll talk about that notion of the so-called positive Grassmannian in the next part of the lecture. But it's not just one subspace; it's a whole family of subspaces, continuous family of subspaces with some positive restrictions. But anyway, you can move it around continuously, but I have this form that lives on the whole big space, lives everywhere in the whole big space, but that form is completely dictated by the requirement that when you pull it back to the subspace, that form has singularities, these logarithmic singularities on and only on the boundaries of this intersection that ends up, none of this is supposed to be obvious right now, but the intersection of these subspaces with the positive part is a positive geometry. It has this feature of having boundaries of all codimension and of having a canonical differential form with singularities on and only on its boundaries. I should say that this is the subject of these ideas of positivity in Grassmannians and so on. That's something that's been explored by mathematicians, starting the mid to late 2000s. But the extra things that are going in to defining the full amplitude are really new mathematical ideas. So this is also quite new mathematical territory. And so many of these facts about the amplituhedron that I'm just asserting are, they're physics facts, but they're mathematical conjectures. So there's still a lot of work to be done to sort of understand why it all works, prove that it all works, never mind to actually learn to compute these things in very different ways. So that this is not by no means a closed subject from either the physics or the math point of view at all. But I'm just asserting that that's what's true. So as physicists, we care about what's true to begin with, and yeah. So there's this family of subspaces. For any one of these, anywhere in this family, the intersection of the subspace with this positive region is this sort of interesting positive geometry, and the super amplitude is the unique object that has singularities there and only there. There's another question: can the subspaces be thought of as corresponding to different helicity sectors? Yeah, if you like, we have different dimensional subspaces. We have 4 times k dimensional subspaces, so 4 times k plus L dimensional subspaces, but a fixed loop order L, we have subspaces of different dimensions that go up by 4, and those are indeed the different helicity sectors. You see one sort of, perhaps I can make one, maybe I'll make one more point here, and then we can take that break, Son.
Sure.
I just want to give some indication. There's all kinds of things that are lying underneath our noses that that give an indication for a picture like this. Let me give you 2 examples. So let's take something extremely familiar, like this simple box. 1, 2, 3, 4. Okay. So we said that if I write it as a form, it's d4x over x minus x, d4x naught over x naught minus x1 squared, x naught minus x4 squared. Okay. Now, if you look at this, it has a bunch of simple poles. And so you might be tempted to say, I mean, if I give you an expression that looks like dA over A, dB over B, then okay, cool. That's very simple. That's d log A, d log B. Okay. So very naively, if you look at this, you would say, aha, it looks like it's this is something very. In other words, if I give you this expression, it clearly has logarithmic singularities when A goes to 0 and A goes to infinity, and B goes to 0 and B goes to infinity. So if you like, you might be tempted, and we'll talk about this in more detail, but you might be sort of tempted to associate something, a very simple form like this, with a kind of a region of space. After all, if this is A and B, it has a singularity here as A goes to 0, another singularity as A goes to infinity, similarly for B. So somehow you might think that you can associate a form like this with the upper quadrant. I mean, extremely simple in this case, but just some geometric region. Well, what about over here? Well, super naively, you would say, oh, this is d log of x0 minus x1 squared up to d log of x0 minus x4 squared. But this is garbage, because x0 minus x1 squared has units. So this expression doesn't make any sense. I can't take the log of something with units. Okay, so it doesn't. So you might at first think it's something simple like that, but it isn't literally that. Now, let's now look at this instead in the language of our. Let's look at this instead in the language of our momentum twister. And in order to do this, remember, we're talking about this, instead of x0, we're talking about this line AB. And again, we'll be talking about the projective geometry more in a second, but something that's pretty clear is that I can completely, a canonical way of choosing what A and B are is just to see where this line intersects certain planes. For example, I can have the plane 1, 2, 3, and I can ask, where does this line intersect the plane 1, 1, 2, 3? I can similarly ask where it intersects anywhere. Okay, so it's natural to write A, for example, as somewhere on the line, let's say 4, 1, 2. This is just something. Let me write it like this. So A is going to be somewhere on the line 4, 1, 2. So I'm going to write it as Z1 plus XZ2 plus WZ4. And B is going to be somewhere, so it's going to be Z3 plus YZ2 plus little z Z4. So this is just saying A, specifying what A is by where it intersects the plane 4, 1, 2, and B by where it intersects the plane 2, 3, 4. Okay, and so if I wrote this as a matrix, so here's A and B, just to specify, there's 1, 2, 3, 4. So this would just look like something like this. Okay, so this is just reminding me, A is Z1 plus XZ2 plus WZ4. B is Z3 plus YZ2 plus little z Z4. Okay, so notice there are 4 variables here, X, Y, Z, W, and that's correct. That would be 4 loop variables, but this is the natural momentum twistorial way of parametrizing these loop variables. Okay, and also in this way, D4AB, this measure just becomes nothing other than dx, dy, dz, dw. Okay, so let's look at what this loop was. It's D4AB 1, 2, 3, 4 squared over AB 1, 2 up to AB 4, 1. Okay, and if I just parameterize, if I just put in A equals Z1 plus XZ2, just what I wrote down before, Z4, and B equals Z3 plus YZ2 plus little z Z4. If I just shove this in here, amazingly what I get, this turns into dx over x, dy over y, dz over z, dw over w. Okay? So it is associated with, it is just 4D logs. Okay, this is, now I can actually write this back in terms of AB. I can write this back in terms of AB, sort of more invariantly. This is just with a particular way of coordinatizing A and B, but I can write this more invariantly as, for example, d log of AB12 over AB24. D log AB23 over AB24. So these are these numerators are just the ordinary poles, which we would have written down from our previous exercise in X space for 1 over AB24. Okay, so it is 4D logs. So this ancient object that people have looked at for decades, this simple one loop box, it actually has this hint in it that it should be thought of as associated with the geometric region, because secretly it's just the wedge of 4D logs. Okay, and how do we interpret this, by the way, back in coordinate space? Well, let's look at our momentum twister picture. So here we have 1, 2, 3, 4. This is now the picture in momentum twister space. So AB12 is like x minus x1 squared, x naught minus x1 squared. Those are just the things that we saw before. But we see there's this new interesting line making an appearance, 2, 4. So this line Z2, Z4 is that sort of line in this problem, okay? And what is special about this line? You notice that what's special about this line and also special about this other line, 1, 3, this is a three-dimensional picture, but what's special about this line 2, 4 or 1, 3 is that these are lines that actually intersect all 4 of the lines 1, 2, 2, 3, 3, 4, and 4, 1. Okay, so that means that back in space-time, there are points that are null separated from all 4 of x1, x2, x3, and x4. And actually, had we known to be thinking about this kind of thing, you see, working in twistor space just forces it on you. But going back to X space, we could have also seen it, that this is the correct formula now. It's not the d log of all the x's, but in fact, there are 2 interesting points. I'll call them x star, so which are null separated from all 4. Which are null separated from all 4 of 1, 2, 3, and 4, which are in turn null separated from each other. Okay, so so this box is in fact the wedge product of 4 d logs like this. Okay, so we see that this one loop integrand has this hint in it of being associated with some kind of geometry, because the same way we could think of the square as associated, we could think about dA over A, dB over B is somehow associated with the upper quadrant. So the fact that the loop integrand is 4D logs is a hint of the same thing. And if I go back to tree level, if I go back to this object that we defined, let me remind you what it was. We defined this object involving 5 z's that we wrote the NMHV amplitude in terms of. Okay, remember this thing was delta 4 of 1, 2, 3, 4, a to 5 plus cyclic over the product of all the poles. Okay, now this guy doesn't, this is just a function, right? There's no, it's not a form, it's not anything. It's just a function of poles and singularities in some interesting place. But, yeah, I'm sorry. And so this, remember, was the sum of this 1 I plus 1 jj plus 1. Sum over I j, but this 5 bracket object, sometimes called an R invariant, is expressed in this way. But if I take all the etas and I replace them with dz's, okay, of course, at first nothing happens. I mean, just a trivial replacement. But then something remarkable does happen. This becomes equal to d log of z1, z2, z3, z4 over, let's say, d log of the ratio, the wedge of the, we have 5 brackets that we can write down, and we just take the d log of the ratio of 4 of them. So d log z2, z3, z4, z5, d log z3, z4, z5, z1, the same denominators. Okay, so when you thought of it as just a super function, you don't see anything geometric. But when you think about the super amplitude as a differential form, you see that this building block for the amplitude is actually, this is a somewhat non-trivial identity. Okay, so this is not, you have to work slightly to see this. The connections we'll talk about in the next lecture with the Grassmannian and so on make these things obvious. But if you don't know those things, it's a non-trivial fact that what looks like the 4th power of all of these Grassmann objects out there actually is equivalent to the wedge product of 4 d logs like this. But so again, this fact that the building blocks for the amplitudes are naturally expressed as d logs, wedge products of d logs on kinematic space, is a clue that was sort of sitting there that tells us that we should think about these objects as actually associated with geometric regions. And it was always sitting there at loop level, because at loop level we always had forms in loop momentum space. But it's also there when we bosonize a supersymmetry, when we think about helicity in terms of these forms. It is also there even at tree level, and the uniform statement is about looking for this 4 k plus l form on the whole kinematic.
So this is about the notion of unitarity and locality that you talked about at the beginning of this talk. So when you have, for example, if you have higher derivative terms in your Lagrangians, that's a non-local theory. So this gives us some notion of locality. Also, if you look at unitary operators acting on states, that gives us a unitary evolution for the theory, and that's unitarity. But how do these two notions, okay, at least as far as I understand of locality and unitarity, I'm just trying to see how they relate to the notions of unitarity and locality that you spoke about at the beginning.
Yeah. So there's, you know, when we write down Lagrangians, we have a notion of what local means. Well, we have a notion of both. Actually, let me say it more. When we work with Lagrangians, we make when we work with Lagrangians, we make Lorentz invariance and locality manifest by writing down local actions. When we work with Hamiltonians, we make unitarity manifest. When we have theories, 2 derivative theories, healthy theories, where we can sort of rigorously at physics level anyway pass between the Lagrangian and the Hamiltonian formulation, that we get to have our cake and eat it too, to see Lorentz invariance and unitarity in different formulations. When we have gauge theories on gravity, famously, we really need gauge redundancy in a big way in order to let us do this, right? Because we choose one gauge to make a Lorentz invariance obvious, we choose another gauge to make the passage to the Hamiltonian formalism obvious. And also when we have higher derivatives and so on, a variety of things become obstructed if we try to think about it as a complete theory. We can't extrapolate to arbitrarily short distances, typically because the interaction strengths blow up, and we can't go back to the Hamiltonian formalism. So that's why we don't think about these theories with higher derivatives as sort of making sense by themselves, although we can certainly use the higher dimension operators as sort of local insertions in the usual way we do in effective field theory. And then both locality and unitarity are perfectly fine, so long as we are restricting ourselves to processes where the effect of the higher dimension operators are treated as small perturbations. So it's very clear and it's baked into the formalism what locality and unitarity are when we have Lagrangians and path integrals and Hamiltonian. There's now a separate question. How do these notions show up invariantly in the actual amplitude? You know, the path, if all you care about is amplitude, there are other things that we can get. When you have field theory, we can talk about other correlation functions, we can, you know, go to finite temperature, we can do really other things. If we only care about the amplitudes, if we're only looking at amplitudes in field theory, let's say you only have the amplitudes. The question is, how are these principles of locality and unitarity reflected in the amplitude? And this is now a trickier question. Well, Lorentz invariance is obvious. You just look to see whether things are functions of Mandelstam invariance, or you just check that it's Lorentz invariant. Also, unitarity is easy. In principle, if someone hands you the answer, you just check that S dagger S equals 1. Okay? The hard part is actually causality. In other words, the Lorentz invariance that we see in the amplitude is just acting on the asymptotic states. So that's of course a beautiful thing, that the full Lorentz invariance has a nice action just on the states that we see out on the at infinity. But because we're not manifestly talking about some local description of the Lagrangian or something that happened in the middle, the hard part is ensuring that whatever we get is somehow compatible with causality. And causality is reflected in the singularity structure and the analytic structure of the amplitudes. And that's exactly the thing that we don't have an ab initio understanding for in complete generality, even in perturbation theory. As I mentioned, the situation is easy at one loop. The situation is easy at tree level. At tree level, we just have amplitudes. They are the only analytic structure they have is poles, and locality just tells you where those poles are. The poles should only look like something like 1 over p squared, where p is a sum of the subset of the momenta of the particle. If someone told you that they got some amplitude by summing all the Feynman diagrams, even without working, you could check if they were lying if it had an expression that looked like 1 over p squared q squared minus r squared t squared, something like that. Then that's garbage. That's not a local pole. That doesn't correspond to a local process in space-time, and you also never get it from any Feynman diagram. So the entire purpose in life of the Feynman diagrams is to make this locality manifest as possible. And at tree level, it's just that we have singularities that are only poles. So that's locality at tree level. Is that the singularities only have poles. Unitarity at tree level, just a statement that S dagger S equals 1. Unitarity at tree level just tells you that you factorize on the poles. So the amplitude on the pole, 1 over p squared, as p squared goes to 0, it factorizes, as Mark explained, it factorizes into the product of two lower amplitudes. Okay, so we know how to check both causality and locality and unitarity at tree level very simply. We also know at one loop, at the level of the full amplitude, we know what kind of functions have to make an appearance. The dilogarithms and higher dimensions, general polylogarithms. So that's under good control at one loop. And it's a frontier to figure out what the rules are at two loops. Okay, so never mind non-perturbatively, we're even trying to understand what the kind of objects are, the kind of functions are that are going to show up at the two loops. That's at the level of the actual amplitude. But at the level of the integrand of the amplitude, things are basically as simple as they are at tree level. The reason is that the amplitudes, again, only have poles. So just rational, the integrand only has poles. It just has rational functions. And so we can again check what unitarity means. For example, let me see if I can, for instance, can you guys see my screen? No, hold on. Let me just.
No.
For instance, something that you're probably used to, folks, is the there's a sort of general statement of the cutting rules and unitarity. So, for instance, at one loop, it's a statement that if you have a one loop amplitude, if you put two of the legs on the inside on shell, that the residue on, so this is some rational function. It depends on L. So if you look at a residue where, let's say where L squared goes to 0, and this is 1, 2, 3, 4, and L plus P1 plus P2 squared goes to 0, that this should, as L squared and L plus P1 plus P2 squared goes to 0, this should look like the product of those two things. So, and when I strip off those two poles, what I should get is the product of two tree amplitudes. Okay, so 1, 2, 3, 4, where now I have these intermediate states are now on shell. Okay, so so you've seen that in the context of the optical theorem and other things. So that is that's a concrete constraint that the one loop integrand has to satisfy. This rational function, it has to poles in prescribed places, and the residues on those poles have to factorize into lower objects in order to reflect that S dagger S equals 1. Okay, so so locality and unitarity at the level of the integrand are easier to control. That tells us where the poles are. Once again, I can't have poles in random places. It's not a pole in like L squared, P2 plus P3 squared minus, it's not some weird combination of L's and the Mandelson variance. It's just when L squared goes to 0. Or in other words, all the poles have to have the interpretation of some line in the diagram going on shell. So that's locality, and unitarity is a certain factorization on those poles. So that's the main reason we can make more progress by trying to control what the singularity structure of these rational functions is. And in a sense, the whole story that I'm talking about is the following. Locality and unitarity imply this very rich, on the one hand, they imply this sort of this rich panoply of constraints from on the singularities and the residues on the singularities of the amplitudes. The great thing about it is that you can use that as a proxy to check whether a result is right or wrong. And also, if you're going to try to get these objects from another place, they had better reproduce these conditions. In a sense, the entire story is that there's very natural and simple questions. Once you get in the right headspace, there are natural and simple questions you can ask in kinematic space that actually ab initio spit out some geometric region where every single one of the boundaries of that geometric region map to every single possible singularity of scattering amplitudes. And not only that, there's an object that's completely determined. There's this canonical form that's completely determined by all those singularities, and that object turns out to be precisely the amplitude. Okay, so that's why it goes from a very vague question to a very, very, very concrete question, and one where you can easily check if you're wrong, which is you have to make a guess in kinematic space, somehow any guess that you like, but it has to satisfy something. It has to produce objects that satisfy these very rigid consistency conditions of having poles in the correct spot and factorization on the poles. But in a sense, the development of the modern aspect of the S matrix program was exploiting locality and unitarity. The sort of height of this is the DCFW recursion relation. You exploit locality and unitarity, find this extremely efficient and beautiful way of determining the answer recursively, only using on-shell data, never referring to Lagranges or anything else. Okay, So that's wonderful, but you're exploiting locality and unitarity. You're taking them for granted and exploiting them. And that's why sort of BCFW is a halfway point between the standard way of thinking about field theory and this sort of positive geometric way of thinking about things. It's a halfway point because it expresses the objects in this sort of pregnant with meaning way of these things that have all the symmetries. They're not individually local or unitary. But what in the end, so it gives you the right building blocks. But in the end, the reason you're putting those building blocks together in the way that you are doing is because of locality and unitarity. You're still tethered to those notions, and you're exploiting them, and you're using them to determine the answer. The story of the positive geometries and the amplitude and their generalization cuts that cord, and it gives a different ab initio starting point from the other side, directly from the side of the kinematic space, and a question in that space that gives you locality and unitarity, and a number of other things, and makes a number of other properties manifest as well. So that was a long answer to your question, but it's a very important question that when we have Lagrangians and Hamiltonians, we know exactly what we mean by locality and unitarity. When we only have the amplitudes, we know what we mean by unitarity and Lorentz invariance, but locality and causality are not obvious. And that's a very deep problem. It's a very, very deep problem to try to understand what that singularity structure and analytic structure of the amplitudes actually is that reflects those notions. The attitude that we're taking now is opposite to the attitude of the S-matrix program. We want to guess some structures in kinematic space that's just going to give us the answer, and then we want to read out of the answer that it is causal and local and unitary, not to go the way they were trying to do it back then. It's a fundamentally sort of both more adventurous and more risky thing to try and do, but anyway, that's what we're doing. We'll be seeing an example.
Thank you.
Nima,
Yeah.
I guess you've taken a break by answering these questions. So why don't we take like just 10 minutes break and we can resume? Yeah, I mean, if you want, you can keep answering questions, but I just want to tell everybody that.
Sure, okay.
Officially, we can take a 10 minutes break.
Good, 10 minutes break, great. I'll be back.
All right.
Yes, I'm ready.
Okay, great. So yeah, so we're happy to have Nima to continue. So Nima, why don't you take over?
All right, great. So now we're gonna come crashing back to Earth here, very practical and sort of nice, to some very practical and nice and pretty things. I want to spend the next little while on a crash course on projective geometry. Projective geometry is the most ancient kind of geometry. Well, sorry, it's not the most ancient kind, but it goes back to the 1500s. And you all in principle know it. Everyone knows about projective space. It's a very simple thing, but it's one of those things that if you're going to think about this subject, you have to know more than what the definition of projective space is and so on. Even though it's all really almost junior high school level stuff, but you have to be able to live there and actually be comfortable in projective space and thinking projectively and so on. And I just want to spend a few minutes on this. More than a few minutes on it, but I want to spend some time talking about it because I find it's one of the sort of main barriers to entry of people thinking about this kind of stuff. So we're going to talk about. I'm going to do a little crash course in projective geometry 101. And again, there are many motivations, but just one of them is very simple. We've already seen that just the data of the external particles is represented in terms of endpoints in P3, and that we have to think about lines in P3 corresponding to points in space-time. We have to intersect or not, and so on. So these are all the geometry there is in our kinematic space, and this momentum twistor space is the projective geometry. There's no notion of metric, no length, just incidence relation. Okay, so let's begin with the sort of simplest definition I'm sure you all know. The projective space Pn is the space of all lines through the origin in n+1 dimensions. And sorry, I should have just said one more general point. What I'm talking about now is actually really more usefully applicable than just the context that we're talking about. Every time you have any question in geometry that does not explicitly involve distances, the way to think about it is projectively. And it'll make your thinking about linear algebra easier. A lot in your life becomes easier when you think about non-metric geometric questions projected. Okay, so all right, so we just gave the definition of Pn. So for example, P1 is the space of all lines. So here's a two-dimensional space, and we have the space of all lines through the origin. So I can think about a point in P1 as being specified by some vector, I don't know, xy. That vector would be a point along this line, but I only care about the line. So all of these points are on the same line. So I identify xy with any multiple of x times y. Okay, and so if I have a generic point, then I can label almost all of these lines, for example, by saying where they intersect. Let me label this, I don't know, y and x, and I'm going to say where they intersect x equals, let's say, 1. Okay. So almost all of these lines will intersect. Almost all these blue lines will intersect the red line somewhere. I'm just going to label all of them by those intersection points. So said more algebraically, I can always use if so long as x is generic, so long as it's not 0, no matter what it is, I can find a t to rescale it to 1. Okay, so I can use this to scale it to like 1 some y hat, and so then I can label where these guys are with that y hat. All right. Of course, this famously, this doesn't cover all of the space because I also have the points that look like 0y. So the point 0y, I can't describe in this way, and that's because the point 0y just don't intersect the red line. All the points 0y are down here, and so these two lines do not intersect each other. But that's fine. That's just the fact that this coordinate chart covers part of the projective space, and I can use another coordinate chart to cover the whole space if I like. All right, so that's P1. Let me immediately go to P2, which we'll spend most of our time on, just because there's more nice geometry and intuition there. So for P2, I have some origin in a three-dimensional space, and I have all the space of all the lines through the origin in P2. And again, I can imagine taking this picture and intersecting it with some plane, and the intersection points are just points in 2 dimensions. So that's why it's a two-dimensional space. So again, I can think of this as x, y, z up to rescaling t. Actually, let me switch notations. So I have some point xi. This is a vector, and I can write this as z xy. But I'm supposed to identify xi with t times xi, and I can use this, for instance, to rescale z to 1. and then I would have 1 times just a 2 vector xy. Okay, so all right, now what's the point of it looks like we're just talking about the plane. So what's the point of thinking about the plane in this one higher dimension way, where we think about, instead of the points on a 2-dimensional plane, we think about lines in a 3-dimensional space. And the point is that actually there's a hidden symmetry of an ancient, this is an ancient thing, but there's a hidden symmetry in configurations of just points and lines in the plane. Okay? And the hidden symmetry is the following. So so let me first pretend we didn't know anything about this projective, about this P2 picture, and let's just ask the following question: in the plane, what symmetries map lines into lines, straight lines into straight lines? Okay, and the obvious answer is, well, I can do 2x2 linear transformations, SL2, and I can do translations, T2. And those are the obvious symmetries that map straight lines into straight lines. But they're not the most general symmetry that maps straight lines into straight lines. The most general symmetry that maps straight lines into straight lines, the most general one, is actually SL3. So it's an SL3 symmetry that maps straight lines into straight lines. And this SL3 symmetry, so if you like, the SL2 here to here, we'd have X goes to some 2x2 matrix X plus a translation T. But there's actually a bigger symmetry, an SL3 symmetry, which acts non-linearly on the X's. X goes to Lx plus T over, let's call it, I don't know, B dot X plus C. Okay. So I have this interesting nonlinear transformation. This is reminiscent of the Mobius transformation that you're familiar with. Many of you are familiar with just in P1. But this is a transformation that also, despite the nonlinearity, it also maps straight lines into straight lines. But it has the following beautiful feature: the SL2 cross translations have the property that if you have 2 parallel lines, they continue to be parallel after you do the SL2 cross T2. However, the most general transformations, SL3, don't respect the notion of parallelism. So if you have 2 SL3 transformations, the new lines might intersect each other. They'll still be straight, but they intersect each other. And this SL3 transformation is completely obvious from the projective picture, because in the projective space, I have an obvious SL3 symmetry, just the linear transformations that act on these lines. Okay, so I just have the I have the linear transformation. The SL3 symmetry is obvious. And what that symmetry does is it takes Z, X, Y, and it takes a general 3x3 matrix that acts on Z, X, Y. If I rescale Z back to 1 after the transformation, then I get this nonlinear. So this is just a simple 3x3, a general 3x3 transformation on Z, X, Y. But if I start with 1 XY, I will not go after I do this. I will have something up here, some funny Z star X prime Y prime, and then I rescale that back to 1 X prime over Z star Y prime over Z star, and that's the action of the SL3 that we just talked about. Okay, so there's a nonlinear action of the SL3 purely described in terms of variables on the plane that's trivialized as just linear transformations on the space of lines through the origin. So that's apart from it being very elegant, this projective way of thinking about points in the plane manifests this extension of the SL2 cross translations that has the property of mapping straight lines into straight lines. Okay, now, but the real utility of the projective way of thinking is that we can uniformly think about all aspects of the geometry of intersection and incidence without thinking, just keeping track of just writing down the only objects we can, keeping track of where the indices are, and every expression that you write down, which has the correct indices, is the right answer to any question that you're interested in. So let me give you some examples. So let's begin with describing lines in 2 dimensions. So lines in the plane. And by the way, if you want to visualize anything we're doing in PN, just imagine Rn, because that's all that's going on. Is that the sort of data is exactly the same as Rn, but there's this bigger symmetry that's made manifest by adding this one extra component to the vectors. And as we'll see, this one extra component also makes it much easier to think about all of the geometry. So how do I normally think about the equations on a plane? I would write down, for example, a line is ax plus by plus c equals 0. But if I want to think about this projectively, I actually think of this as the equation ax plus by plus cz equals 0, where I've used my freedom to rescale. I've used this freedom to scale z to 1. Okay, so this is called the sort of homogenized version of the equation. So now in this form, the action of this the action of the rescaling is manifest, and I can use it to set, for example, z equals 1. Okay. Now something else I should have said is that we have this we have the points in P2, or this xi. These are points with I runs from 1 to 3. The SL3 that we just talked about is xi goes to just a completely general, we call this curly L, ij, xj, where this is just a completely general 3 by 3 matrix. And the only invariant tensor is epsilon ijk. Okay, so just to say something about this, right now we're going to be coming back to this kind of thing over and over again. If I have 3 points, x1, x2, and x3, what is the kind of invariant that I can talk about? Again, how close or far they are doesn't mean anything. The only thing that does mean something is if they happen to lie in a straight line. So if they're collinear, this means something, and the collinearity tells us, what does the collinearity tell us? It tells us that I can write, for example, x3 as a linear combination of x1 and x2, and therefore this bracket x1, x2, x3 is equal to 0. So the invariants that I can make using the epsilon symbol, for example, if I have 3 x's, I can contract them, and the overall magnitude doesn't mean anything. Why doesn't the overall magnitude mean anything? Because I can rescale each x. So the magnitude doesn't mean anything, but it does mean something if it's 0. And if that invariant is 0, it means that the 3 points are collinear. Okay? Okay, so now let's go back to talking about the lines. So notice that I can now think about a line as simply an equation that looks like this: Li xi equals 0. Okay, where now my xi was zxy, and now my Li was cab. Okay, so what we see from here is that if the x, the x is a point, it has an upstairs index, the line is something with a downstairs index. So upstairs point. Okay? And this equation now is perfectly homogeneous. So this is a legal equation. The equation is invariant under rescaling x. It's also invariant under rescaling L. So this is a perfectly sensible equation in projective space. Now, why is this useful? So let's now think about the following question. So suppose I give you suppose I give you 2 points, x1 and x2. Okay, so here's x1i and x2i. I want to know what is the line. What is the line that is formed by those 2 points? Okay? Here's the answer to all such questions. You take the objects you have and you put them together with the invariant tensors in the only way you can to make something with the correct indices. So I'm looking for something that is a line that depends on these points 1 and 2. It's a line, so it should have a downstairs index. So the only way I can do that is to contract with an epsilon symbol. Okay. So that explicitly gives me an expression for, it's clearly a line. Furthermore, I can check that x1 and x2 are on the line. How do I check? Well, let me look at Li x1i. Well, this is epsilon ijk, x1i, x1j, x2k, and that's equal to 0 because of the antisymmetry in these indices. Okay, so I conclude that x1 and x2 are indeed both on that line. Okay, so good. So we learned how to build, just write down immediately, the line that connects 2 points. What if we want to go the other way? What if I have 2 points? What if I have 2 lines, L1 lowercase I and L2 lowercase I, and I want to know what point do they intersect at? So now there's some point x12, and well, it's exactly the same thing as x12I. Now I have to put the lines together. Is epsilon ijk, L1j, L2k. It's exactly the same thing. That gives me the point that that lies on those 2 lines. Okay. In fact, in this way, we can talk about what we normally do when we don't think projectively. What we normally do is we think in terms of the so-called affine plane. So that's again when you don't have a notion of a metric, but the only symmetries that you have are the 2x2 linear transformations and translations. To see what's going on, let's ask what happens in the language that we just talked about. What if we have 2 parallel lines? What if I have 2 parallel lines? Well, what are the equations for the parallel line? Maybe this equation is ax plus by plus c equals 0, and this is ax plus by plus c prime equals 0. So evidently these two lines are parallel and they don't intersect each other. But by the formula that we just wrote down, we can find where they intersect projectively. Okay? So what am I supposed to do? So here's L1 is CAB. This is L1, I, L2I is C prime AB. And so where are they supposed to intersect? Is this X12 is epsilon ijk L1, oops. And just these backwards. X12 is epsilon ijk L1j L2k. And what is special about this is that you see that the top component of this guy is equal to 0. So whatever this is, this looks like 0 and A, C minus C prime, and B, C prime minus C. I'm not screwing up the signs there, but the important part is that the top component is equal to 0 because these 2 bottom ABs are equal to each other. So we see So what do we see? We see that the point that they intersect at, the top component is equal to 0. Well, remember, we are implicitly assuming in writing all these things down that we'd rescaled the top component to be 1. Okay, so the top component actually being 0, if I want to rescale for the top component to be 0, then I have to multiply all of this by 1 over infinity. If I want to, and so saying that the top component is 0 means that x and y are becoming infinite compared to 1. Okay, so this point is, so this intersection point, 0, anything is actually at infinity. And in fact, we can think about the usual, points, more invariantly, the usual points 1, x, y. A more invariant way of characterizing it is to say that there's a special line at infinity, L, let's say infinity, I, which is equal to 1, 0, 0. And the part of the projective space that we're covering with the ordinary coordinates are exactly those points where x dot L infinity is never 0. In fact, we're setting it equal to 1, but we're saying that x dot L infinity is not 0. In other words, the points that we're covering with 1, x, y are precisely those points that are not on this line at infinity. But invariantly, all that's going on is that we have this projective space. We can decide to put some privileged line at infinity if we like. If we do that, this breaks the SL3 symmetry down precisely to SL2 cross translations. It's just a subgroup of SL3 that leaves this vector 1, 0, 0 invariant. So you can really think about this kind of like the Higgs mechanism in grand unified theories. You have this very symmetrical space with an SL3 symmetry. If you decide that there's a privileged line at infinity, that choice breaks the symmetry down to SL2 cross translations, the symmetries of the affine plane. You can go further and specify further invariants, and that further reduces the symmetries still down to rotations, or depending on if you're doing real or complex projective space, O1, 1 Minkowski space. So even the metric comes from a natural further notion of invariance to hold fixed in this projective way of thinking about it. But anyway, we're not talking about metrics. So the choice of a line of infinity is what determines this affine part of the space and breaks. If we hold it fixed, it breaks SL3 down to the affine symmetry. So all that's going on is, so the notion of parallel or not parallel is said projectively. Generically, two lines will meet at a point. All lines meet. All pairs of lines meet at a point now projectively. There's no exception for parallel lines, but parallel lines projectively are things that meet on this line at infinity. And the final sort of historical comment about this is that this is one of those cases where art preceded science. One of the stimulations for thinking about things this way was when painters in the 1500s started learning to draw in perspective, and they started realizing that it's useful to have a horizon where all lines met, the way you literally see things when you look, and trying to think about what that was doing mathematically was an impetus for people like Desargues and others to start developing projective geometry. Okay, so that's just so we will not typically be talking about this line at infinity, but just so we talk about how that how the usual affine space fits into the story. Okay, let's do some other quick examples. So let's say, just going back, just doing this a little more detail. Let's say that someone actually gave you 2 points 1 and 2, and another 2 points 3 and 4, and you want to know what is the intersection of these two lines. So we already figured out how to do 1, 2, and 3, 4. So in principle, again, we know exactly we know exactly what to do, but I want to illustrate how everything you do is just not thinking. Okay, so I want to find 1, 2 intersect 3, 4. Somehow I have to get something with an upstairs index, and it should also only know about the line 1, 2 and the line 3, 4, not about the points 1 and 2 and the points 3 and 4 separately. So anything you do with the line 1, 2 should be invariant under 2 by 2 linear. If I take 1 and 2 and replace them by linear combinations of 1 and 2, I should get the same answer. So any expression should be antisymmetric in 1 and 2 and antisymmetric in 3 and 4. So for instance, this is x1 times this bracket 2, 3, 4 minus x2 times this bracket 1, 3, 4. Okay. This is also equal to negative x3 times the bracket 1, 2, 4. I could do it the other way around, plus x4 times the bracket 1, 2, 3. Okay, so that's so this is an expression. You see, it's antisymmetric in x1 and x2. It's antisymmetric in x3 and x4 on this side. Right. So anything you do is just the only thing that you can do with the correct indices. Now let me make a general comment in any PN. In any PN, there is a sort of very basic fact that I can take any n+1 vector and expand it in a linear combination of some basis set. So, for example, let me just do it even in P1. I can take any vector. I can take any 3 vectors. I can take 2 of them and write the third one as a linear combination of the first 2. Okay? And in P1, this is the identity that x. Let me write it like this: x1I times x2 x3. So in P1, the bracket is just is a 2-dimensional epsilon symbol, and it's anti-symmetrized. It's minus x2I, x1 x3 plus x3I, x1 x2 equals 0. Okay? So this is sometimes called the Schotten identity or Kramer's rule, but anyway, all it is the fact that I can express any vector as a linear combination of any 2-dimensional vector as a linear combination of another 2. In P2, it's always the same. It's x1i, x2, x3, x4 minus x2i, x1, x3, x4 plus x3i, x1, x2, x4 minus x4i, x1, x2, x3 equals 0. Okay, and I'm writing this down because this Kramer's rule or Schotten identity also gives us an interpretation for the formula that we just wrote down. You see, I can think of this as telling me that this is equal to negative that, and that's just what we saw, right? That's just what we saw. That's just the interpretation that the intersection of the line 1, 2 with 3, 4 can be thought of either as in terms of the either in terms of the linear combination of 1 and 2 or in terms of the linear combination of 3 and 4. So we can interpret this Kramer's rule formula as a way of reading all the possible intersections that involve those n+1 points and all the different planes you can make of different dimensionalities between them that intersect. All right, now let me just give one more example. These examples are essentially trivial, although they make thinking about just practically they make thinking about the linear algebra in this business much easier. All right, so let's just do another fun example. It has a little more meat. Let's look at conics. So what's the general equation for a conic? Again, it's A. So this is the way you would normally write it down. And once again, we will projectivize just by adding a z everywhere. Okay, so now this is a nice homogeneous equation. And so the equation that defines a conic looks like Cij xi xj equals 0. So a conic is something that has two downstairs indices, two downstairs symmetric indices. Okay. Now, so this is already, we can already have some fun. So let's say you have a conic C, and let's say there's a point on the conic, x star, it's on the conic, and say you want to figure out what is the tangent to this point. What's the tangent line to this point? Now, this is already maybe looking like a bit of a pain. You have to think about some derivatives or something. But let's take our newfound attitude and just see what we can do. What am I trying to do? I'm trying to get a line. So how do I get a line? Well, the only way I can take this data together and get a line, there's a line tangent to the curve upstairs is, sorry, it's got to have a downstairs index. And it's just Cij x star j. That's it. And that is correct. And how do we see that it's correct? Because, well, x star is on this line. If I look at Li x star I, it's Cij x star I x star j, which is 0 because x star is on the line. Very good. All right, let's do another example. Let's say I have a point here. Here's a point x, not on the conic. Here's C again. Now, we just wrote this object, right? Cij xj. Well, this is a line. What the heck could this line be? It's associated with the same data, but x isn't on the conic. It's not the tangent to anything, x isn't on the conic. Well, there's only one thing it could be, and it's the following. How do I make a line out of this data? Well, to begin with, I can take x and I can draw two tangents. They touch the conic in 2 points, and then I can make this line. And that's what this line is. Okay, so this, the line Cij xj is exactly given by that. Okay? So that's cool. Without even thinking, you come up with the answer to what otherwise seems like a slightly complicated question, but it's the only object that you can build out of the point and the conic, and so that's what you get. Let me give a final example along these lines. Let's say I have 2 points, and let's ask, what does it mean for Cij xi yj equals 0? What does this mean? So if I have 2 points x and y, well, it means if I so let's say here's x. We already concluded that Cij xi is this line. And so this condition is telling me that y has to lie on this line somewhere. But you see, this condition is symmetrical between x and y. So I can also think about the line from y. So I would draw these two tangents and this line. And you see the remarkable fact that that if y lies on the line formed by the tangents emanating from x, then x lies on the line from the tangents emanating from y. Now that's a sort of classical Greek mathematical fact, but it has this completely trivial understanding, just again staring at the relevant object. All right. Now, in fact, the first non-trivial statements about projective geometry really begin when you start thinking about conics, and I'll just leave this as an exercise for you guys. So it's very easy to see that given 5 points, you uniquely determine a conic that passes through them. And the 5 is just counting. This is just counting the ax squared plus bxy. Well, it's just counting that Cij. We have Cij up to rescaling up to some C Cij. So this is a 3 by 3 symmetric matrix. So it's 6 minus 1 equals 5 degrees of freedom to specify a conic. So given 5 points, we determine these 5 degrees of freedom. So, but here's a natural question. If you have, how do you know, let's say you have 5 points, 1, 2, 3, 4, 5, and they've determined this conic. How do you know whether or not a 6th point, 6 is actually on the conic or not? So what is the condition for 6 points to lie on a conic? And this is actually a beautiful example of thinking projectively, because I take this equation to begin with, and I imagine that I have points 1, 2, 3, 4, 5 up to 6. Now I actually think that I'll switch I and j run from 1 to 3, but let me just switch to a 6-dimensional space of the entries of this 3 by 3 symmetric matrix. In other words, I'm going to introduce a new index A, which is just these symmetrized ij, which I can now take to run from 1 to 6. So in this big space, I have CA XA 1, 2 up to 6 equals 0. Okay? But now, what is this? In this big A space, I can think about each one of the x's as a point, and the C is something with a downstairs index, is a hyperplane. So I'm now asking the question, in this 5-dimensional projective space, because the x's are 6 vectors, in this 5-dimensional projective space, what is the condition that 6 points lie on a plane? The condition that 6 points lie on a plane is just that the 6-dimensional determinant between x1, x2, up to x6 is equal to 0. Okay? So in other words, in terms of these A variables, there's a 6-dimensional epsilon symbol, A1 through A6, x1, A1, up to x6, A6 is equal to 0. And then you can translate this 6-dimensional epsilon symbol into a statement about, you can translate this into a statement about 3 brackets involving the x's. And there are many ways of writing the answer, but in the end, there's a wonderful quartic invariant in the 3 by 3 minors, which is the condition that 6 points lie in a conic, is that the following invariant, and there are many ways of writing it, but this is the one way I remember. These are all meant to be brackets, contractions with the 3-dimensional epsilon symbol. Okay, so this object is actually permutation invariant in the 6 entries up to sign, and this equals 0 guarantees that the 6 points are on a conic. So it's a very non-trivial looking thing, that there's some fascinating quartic invariant that has to vanish, but is really trivialized by thinking projectively. In fact, an exercise for you is to use these ideas to prove the first, what David Hilbert called the first non-trivial theorem in geometry, which is Pascal's theorem, which is the following: if you have 6 points on a conic, so this is one characterization of 6 points on a conic, and it's just a rewriting of the equation that we just talked about. But Pascal's theorem says if you have 6 points on a conic, and you form the following lines, 1b to A, 2c, 3b, and 3a, 1c, that the corresponding intersection points are collinear. Okay, so that's Pascal's theorem, and it's an exercise for you to prove this using these sort of techniques of using the ideas that I was just sketching out. Okay. Now, one final point to make about this projective geometry. Another few quick points. There is a beautiful notion of projective duality. It's the kind of most ancient version of duality. So here's a statement that that any statement on the plane about points and lines is true if you replace lines with points. So there's a duality between interchanging points and lines. Okay? And this is analytically obvious because lines have downstairs indices, points have upstairs indices, and it's completely a convention who's upstairs and downstairs. Okay? So any statement you have between points and lines, you can just say the action of SL3 was L inverse instead of was a matrix inverse instead of the matrix, and you have a new statement where the lines are points and the points are lines. Okay, so this is just the upstairs to downstairs index obvious symmetry. But it is really, it's not super obvious just looking at configurations of points and lines and so on in the plane. For example, the dual of Pascal's theorem is a seemingly very different statement, which is that instead of having 6 points on a conic, you have to replace the points with lines. And so what does it mean? So instead of having 6 points on a conic, I have to have 6 lines tangent to a conic. So the dual of Pascal's theorem is that if you have a conic inscribed inside a hexagon, 3, 4, 5, 6, that if you continue these points, oops, I've drawn it very badly. What's new for today? Okay. That if I, so I extend the edges of the hexagon in this way. And if I now connect these lines, that the lines are pass through the same point. Okay, so this is not at all obviously related to the original statement of 6 points on a conic, but again, they're related by this beautiful and very simple duality that interchanges lines with points. All right, so let me actually take a break there just to see if there are any questions before we move on to a few more things about projective geometry in P3 and some related issues. And any questions? All right. Okay, then let me. You can all hear me, okay, right?
We can hear you, yeah.
Okay. All right. Okay, so all right, so let me now move on to talking about P3, and then the sort of generalizations are clear. Well, one thing that we said already is what is a plane? What is a hyperplane? It's exactly the same, ax plus by plus c equals 0. Plus cz plus d equals 0. So again, we'd add a w there. And so now we have points xi that are like, w, x, y, z maybe, okay? And so the hyperplane is again something with a downstairs index. Okay, so just repeating things we did, if you have 3 points, x1, x2, x3, and you want to know what plane they lie on, they determine a plane, then this plane is h lower I is epsilon I j k l. H lower I is epsilon I j k l x1 j x2 k x3 l. Okay. And so if I want to talk about similarly, if I have some plane, let's say I have a plane made with the points 3, 4, and 5, and I want to know where the line 1, 2 intersects this plane, then this intersection 1, 2 intersect 3, 4, 5 is just the same as we saw before. It's like x1 times 2, 3, 4, 5 bracket minus x2 times 1, 3, 4, 5. And once again, the only bracket that we have is the epsilon symbol. Okay, so if I have 4 points that happen to lie in a plane, if they're coplanar, 1, 2, 3, 4, then that means that x1, x2, x3, x4 is equal to 0. Okay. By the way, this also means that if I, let's say I now want to talk about a line. So if I have x1 and x2, and there's I and I, what is this line? Well, the equation for a line is now going to have 2 indices, right? So and so the line is going to be Lij equals epsilon I j k l x1 I x2 j x1 k x2 l. Okay, so lines are something are antisymmetric matrices with 2 downstairs indices, and in fact, it's not a general antisymmetric matrix because it has rank 1. If I take the determinant of L, if I take 2 L's and I take their if I take the epsilon with itself, I'm going to get 0. Okay, so but anyway, so given 2 points, this is the line that they form. So we can also see from here that another interpretation of these 4 points being on a plane is, for example, that the line, for example, 1, 3 intersects a line 2, 4. So that's just a statement again that 1, 2, that's the line 1, 2, 3, 4 is equal to 0. Well, that's exactly just sorry, I did 1, 3, 2, 4. It doesn't matter. This is just saying that x1, x3, x2, x4 is equal to 0. This is just rearranging the things that we have up there. We just pick up a minus sign. Okay, so we can interpret either as 4 points lie on a plane, or the line x1, x3 intersects the line x2, x4. All right, and so we can go on in this way for projective space in any number of dimensions. Hyperplanes of dimensionality p are just completely antisymmetric tensors with p upstairs indices. So for general Pn, we can, if I take a bunch of points, I can make anything of any dimensionality by wedging these things together, I1 through IP, and then J1 through Jn plus 1 minus P. So these are the general hyperplanes of all possible dimensionality. And in general projective duality interchanges upstairs to downstairs indices, interchanges intersects p planes, p dimensional planes with n minus p with n minus p minus 1 planes. Okay. It's just, again, just moving indices upstairs and downstairs. All right. Okay. Now we're going to move on to a couple of other important projective notions. I want to talk about the notion of area slash volume. I mean, area in 2 dimensions, but volume more generally. Volumes thought of projectively. So this is going to be something that will be useful for us as well. And this is an important point, that while the notion of distance needs a metric, the notion of an area or volume does not. The notion of area or volume is an affine notion and doesn't need a metric. So let's see how this works in a very simple example. Let's go back and think about the high school formula for the area of a triangle. So let's say you have a triangle with 3 vertices, and there are positions x1, x2, and x3. Then you probably remember that the area of this is equal to this determinant up to the factor of 2, which I won't be careful about from now on, is a determinant of this matrix: 1x1, 1x2, and 1x3. We're again allowed to be positive or negative. I'm not going to put magnitudes around it. Okay, so that's the high school formula for the area of a triangle. But we can immediately interpret this formula projectively. This looks like something projective after all. Upstairs, it just looks like x1, x2, x3. If I work in terms of the xi as being 1, going to this 1 higher vector, okay? That's what it is upstairs. But this formula cannot be the area. It has lots of problems. Chief amongst them, it doesn't have units, whereas the area has units. And also, it's not invariant under rescaling x1, x2, and x3. And anything we do in projective space has to be invariant under that rescaling. So the notion of an area does not make sense by itself, but it does make sense when we introduce an extra line at infinity. So if we introduce a line at infinity, then we can actually do the following. We can divide by L infinity dot x1. So this is in the bracket. Remember, L infinity is a downstairs index. So this is L infinity x1, L infinity x2, L infinity x3. This is an expression which does make sense now projectively. If I rescale x1, x2, and x3, it does make sense. Furthermore, it has units, as it should. You know, L infinity carries units. So this allows me to define projectively a notion of area, which depends not just on the x's, but on the x's as well as a choice of the line at infinity. Okay, so this is the notion of the area of a triangle, and more generally in PN, I can talk about the volume of a simplex, like a tetrahedron or higher thing with corners x1, x2 up to xn plus 1. And the volume of that would be x1, x2 up to xn plus 1 divided by, again, the volume depends both on a notion of some hyperplane at infinity and the x's, h infinity dot x1 up to h infinity dot xn plus 1. Perhaps I should have said more explicitly back in this example that if I put L at infinity, like we're supposed to do to get the affine space, then this formula matches the previous high school formula, right? Because downstairs, L infinity dot all of the x's is just equal to 1. Okay? But this is the more projectively invariant way of saying. You'll notice that the area vanishes when x1, x2, and x3 are collinear, as it should. So that's correct. That's when the triangle collapses. What is the interpretation of what happens when these denominators go to 0? So this area can blow up when the denominators go to 0. If I draw it invariantly in projective space, I just have this line, and just giving it a name, L infinity. But this notion of an area is blowing up when one of these corners, let's say the corner 3, goes to lie on that line. Then as that happens, L infinity dot x3 is going to 0. So this area is going to infinity. And what does that mean in the usual affine way of thinking about things? Well, that's just simply the fact that if I have this triangle 1, 2, and 3, and I just take this point 3 and I push it to infinity, then the area is going to blow up, obviously. So, but again, this is the sort of more invariant way of saying this projective. So that's something to keep in mind, that we do have a notions of volumes projectively, but they need this notion of an infinity. Okay. Finally, another comment is about differential forms in projective space. So we're going to be talking about this as well. I've already foreshadowed that we care about this in the kinematic space. So let's ask about differential forms in projective space. Okay, and first let me let's start with something simple. Let's start with P1. Okay, so here we have like xy, right? That's our 2 vector, and we want to think this is up to rescaling the same as t times xy. So for instance, it's pretty clear that that if I use this to if I use this to scale xy, let's say to 1y hat, then what should a form be? Well, clearly, if I write down dy hat times some function of y hat, this should be okay. That's what you would think. But we want to sort of understand this more. We want to understand this more invariantly, and so let me try to write down. Let me just try to write down a form, and see how it can make sense. So let's first do the sort of most naive thing that you could do. Like, let's say you have dxi. Well, anything that I do has to be SL2 invariant, so I can't just leave that index hanging. Well, what I can do is multiply by xj and take epsilon ij. Okay, so we'll sometimes contract this as x dx. Okay, that's a perfectly nice thing to do. And so, for example, here's a form that I could write down. I could write down x dx, just to give an example, over xa xb. And even this thing, it now looks at it as perfectly fine weights under x. There are 2 x's upstairs, there are 2 x's downstairs, so it's invariant under rescaling x. Maybe I can even fix up a and b upstairs by multiplying by ab. But anyway, so that's a perfectly reasonable looking form. And let's see how it works. So what is this x dx? Remember, x, now I can choose my homogeneous coordinates to look like, sorry to switch notation slightly here, but let me say I make it look like 1 little x. Then dx is 0, d little x, d of 1 is 0. So dx is 0, d little x. So epsilon ij, xi dxj is just dx. Good. And so if I put a is 1 alpha and b is 1 beta as well, then this form would become, for example, dx times beta minus alpha over x minus alpha, x minus beta. Great. Okay, we're very happy with that. Okay. So this kind of looks funny at first to have this x lying around in this measure, but it's necessary it's necessary here just to make something projectively invariant, SL2 invariant. And as you see, after you homogenize, after you sort of go to a particular coordinate chart, it turns into the sort of obvious dx like like measures that we're used to seeing. But there's something else that we could have done. Why couldn't we do the following? Why couldn't we have taken, let me take some other random vector, the c. Why couldn't I have contracted c dx over, just xa, for instance? That has all the weights in x are fine. Okay, the weights in a and c we can fix up some other way. I can write down some a b over cb, for example. I could even do that, although it's not really relevant for this. It's not necessary for the point I want to make. Anyway, this is a perfectly reasonable looking form as well. It's invariant under rescaling x, and a, b, and c, everything looks fine. But this form is garbage. It's actually not really well defined on the projective space. In order to see so, let's just see one problem it has. Let's say I put c is 1, 0. Then if I choose the coordinates, the coordinate system where x equals 1 little x, then this c dx is indeed d capital X is indeed equal to d little x. But if I choose x equals y1 instead, another coordinate choice, then c dx would equal 0. So that can't be right. The form can't be 0 or non-zero depending on the coordinates that you choose. And the problem is that it is actually not enough for the form merely to have the correct weights under global rescaling of the x variable. You see, the problem is that when you're trying to define a form, a differential, you have to compare x at nearby points. So I have to compare x here and there. And so I'm thinking about sort of lines through the origin for both of them, but the x at this point and the x at this point and the x at this point have to be invariant under their own private rescalings. So in other words, for a form on projective space, we have to have an invariance under a local GL1 transformation where xi goes to t of x xi. And let's see why that. So clearly this dumb example fails that, right? If I take c dx, then under x goes to t of x xi, dxi goes to t of x dxi plus xi dt. And so c dx goes to t times c dx. That part is good. It can cancel against the denominators and so on. But it has this extra piece, which is cx times dt. And this is a disaster. This is bad. It's not invariant. But how does x dx solve that problem? See, x dx beautifully solves this problem because this goes to t times x dx plus, and now this dx is being replaced by x, which contracts with itself to give me 0. And so that's how I see that every form on projective space, every form on P1, which is invariant under this local GL1 action, has to look like omega equals x dx times some function of x that has weight minus 2. That weight minus 2 is just to eat up the weights under rescaling rescaling the x's here. Similarly, every form in Pn has to look like x wedge dx dx dx, all contracted with the epsilon symbol, times some function of weight minus n plus 1 in the x's. And note something quite nice here. We're contracting all of these things with epsilon symbols, so they would naively vanish, except the dx's themselves are forms. They're anti-commuting. So so that this contraction gives me something sensible. Okay. All right. So so we've also learned how to talk about. So we've learned how to talk about volumes in projective space, and also how to talk about differential forms in projective space. And maybe I can pause again to ask if there are any questions.
And I have a question, Nima.
Yes.
So this is completely independent of whether you are in some Riemannian manifold. I mean, all this will just go through. I mean, I don't know how to say it, but if the larger space is a Riemannian manifold rather than a linear space, will this all go through? I mean, this type of.
I'm not sure what you mean by this all. I mean,
this all means all these formulae that you're talking about in terms of differential forms. We know do not care about the metric.
That's right. Yeah, differential forms don't care about the metric, but we can write down in principle on general spaces, we can write down zillions of differential forms. What I'm talking about is how to write down forms on forms on projective space. So it is special to it is special to projective space. It is special to that means so. That there would be nothing wrong on some. I mean, if I say it invariantly, nothing stops me from writing down a 2 form. Let me say it another way. Nothing stops me from writing down a 2 form on the plane, even. Okay, I can write down a random 2 form on the plane, but and those 2 forms, you know, if I preserve SL2 in translations. Okay, they're compatible with the affine structure on the plane, but not a random 2 form on the plane lifts to something which is actually SL3 invariant. Remember that SL3 purely in the language of the plane is a nonlinear symmetry. What we're doing is completely linearizing the action of that SL3 by imagining that we go up to this 1 higher dimension. But in this 1 higher dimension, we have this local rescaling symmetry, and so therefore. In order to be compatible with this, in order to be compatible, both of the ability to go back down to 2 dimensions, as well as to have the SL3 symmetry, you have to write down these rather special forms with this structure we're talking about. So this is beyond the fact that differential forms are coordinate independent. Yeah, it's beyond the fact that the forms are yes, it is beyond the fact that they're coordinate independent.
Okay, thank you.
Yeah, or maybe I could say it yet another way. If I took this bad form that I wrote, there's nothing. You see, this is a 1 form. This bad form that I wrote is this was a CDX. This bad form is the 1 form on a 2-dimensional space. And now what am I doing when I write x equals 1y? I'm pulling back this form to different 1-dimensional subspaces. Now, nothing guarantees that I get the same answer if I pull back to different subspaces. That's why if I just think of this as a form living on a 2-dimensional space, there's nothing wrong, even with the bad one. However, it's my desire to think about the 2-dimensional space in a way where I can do linear transformations that map any line to any other line. It's my desire to have both the SL2 symmetry as well as the, more importantly, as well as the sort of rescale invariance, so I only care about the lines, that forces me to have the structure that I want.
Okay, thank you.
Nima, we have a question in the chat room.
Okay.
Can you see it?
Yes. Is the question, is there a way to describe self-dual forms in this language?
Yes.
Absolutely. I mean, it's. I'm not sure what you mean. Yeah, that there is, for example, in P3, we can talk about what duality means in a P3. In P3, a point gets mapped to a plane, but a line is mapped to itself. So lines are self-dual in P3. And again, it's just the counting that we can have either one upstairs index as a point, which by duality is the same as one downstairs index that is a plane. Two upstairs antisymmetric indices is a line, which is the same as two downstairs antisymmetric indices. So that's why lines are self-dual. Okay. All right. So,
can I ask a question as well?
yes.
Will you be generalizing these to complex numbers also?
Oh, this is all. I mean, I should have said everything here does not depend on whether it's real, complex, or anything. But to draw the pictures, it's useful to just draw them in real space and to think about it in real space, and you always get the right answer when you do that, sort of for obvious reasons. The reason is that all of these expressions are sort of trivially analytic in the variable. So anything you do with these incidence conditions and determinants vanishing and this and that has nothing to do with whether nothing to do with whether things are real or complex. So you can sort of visualize what's happening by literally thinking about them as points and lines and planes and so on in 3 dimensions. Yeah. That being said. Later, when we start talking about positive geometry in these spaces, we will really be thinking that they're real, even real and positive. There's a notion of positivity as well. And I should say that's going to end up corresponding to data, kinematical data that actually lives in 2,2 signature. So when I told you that there's some region in the kinematic space that's positive and so on, that's all going to be, that positive real region is all going to be living somewhere in 2,2 signature. However, the differential form that is locked by that geometry makes sense everywhere in the complex, in particular in Minkowski signature or for any complex momenta as well.
I see. Okay. So is there also going to be some sort of holomorphic structure?
Very much so. Yeah, we're going to be talking about these analytic holomorphic forms. Absolutely, and they have poles and residues and so on. So that's one of the sort of novelties of this subject, is this strange mixture of real positive even geometry and complex forms. So we have things like triangles and polygons, these ancient sort of Greek, almost Greek kinds of geometric objects, but associated with them are certain complex differential forms. We don't have, at present, we don't have an intrinsically complex way of thinking about what these forms are. They're really tied to these real geometries, which is a rather unusual thing.
Thanks.
But that'll become clear when we start talking about positive geometries and their canonical form. Okay. All right. So maybe I can. There's one last set of things that I want to talk about in the sort of general projective geometry 101, and then we can take a little break and come back for the last part of today. Does that sound good? Is that okay, Yutin and Song?
Yeah, sure, no problem. Yeah.
Okay, great. All right. So, okay, good. All right. So let me now talk about a final set of sort of classical, simple projective ideas. I want to talk about Grassmannians. And so one, we've been talking about we've been talking about the space, for example, of lines through the origin. That's projective space. But if you're going to do that, it seems natural to just generalize. We can talk about planes through the origin, for example.
Could you please share your screen?
Oh, sorry. Yeah. Okay, so we talk about the space of more general K-planes. So this is lines through the origin. So we talk about the space of K-planes through the origin. All right. And now, if you're someone like me, who's not particularly mathematically sophisticated, this just seems like one of infinitely many egghead things that mathematicians like to think about. But let me give you a couple of interesting physical motivations why Grassmannians should matter at all in thinking about scattering amplitudes. Why are these sort of fancy schmancy things, maybe not that fancy schmancy anyway, but why are they showing up? So I want to do a little physical detour, some physical motivation. And this is also serves to highlight what extremely basic ideas are involved in this entire subject. But so I want to go all the way back to thinking about null momenta, okay? Just the data that labels the scattering process. What is the data that labels the scattering process? Let's go back, forget about momentum twistors, all of that fancy stuff. Let's just go back, and we're going to talk about lambdas and lambda tilde, okay? So this is,
Nima?
yes.
So I have a question about this form x dx. So if I want to if I want to have that form around some point, like let's say x is a plus y and y is small, it seems like I'm going to run into sum of two terms where one of them is going to be a dy. I mean, how do I think of that form? Because you just told us that c dx doesn't make sense, only x dx does.
Yeah, I mean, c dx for a literally fixed c does not make sense.
So if I have x dx and if I want to expand it around some fixed c,
yes,
then in the expansion I'm going to end up with forms like that, right? So can I not do the expansion in a projective way?
Well, I mean, the sort of problem is that of course you can do the expansion in a projective way, but what you think of as a subleading term is not small. Again, the sort of notion of big and small is not, you know, your intuitive notion is that 2 points are close. So, but that notion of close is not there in projective space. And
I see.
Yeah. So I encourage you to just do the exercise. Of course, there's nothing wrong with Taylor's theorem. You can Taylor expand anything.
Right.
But what you think of as the next smaller term is not small.
I see. Okay. Yeah. Okay.
Yeah.
Thanks. Yeah.
Right. Yeah. That's in a sense the entire point, right? Is that in projective space, 2 points, even that are very close to each other, you know, they could be in the underlying picture of the line super far apart by doing rescalings differently, right? The whole point of this xdx business is to make sure that it only cares about the line and not about where they are on the line. Whereas what's wrong with the cdx is it privileges exactly what you're saying. It privileges if they're close or not, which is wrong.
Okay, that's great. Yeah, thanks.
Okay. Did that answer your question?
Yes. Thank you.
Okay. Very good. All right. So let's go back and talk about this again. So Grassmannians in kinematical data, and this actually even simpler to see it in momentum twistors, but I want to emphasize how general it is. So let's go back even to ordinary momenta. So we have our PA alpha alpha dot is lambda A alpha and lambda tilde A alpha dot. And so let's just group all of this data together. For example, all the lambdas, I'm going to group in this, here's lambda 1, lambda 2, up to lambda n. Okay, so I can group it into a 2 by n matrix. Let me call this 2 by n matrix capital lambda. Okay, there's the 2. So let's be very explicit. You know, this is like A1, B2, B2, up to some AN, BN. This set of numbers. Now, the way I've just described these numbers to you, I think about this as n column vectors, n two-dimensional column vectors. Okay, so that's just the way we got them. So we group this data like this. But now instead, I want to think about this another way. I want to think about it as 2 row vectors instead. Okay, so I want to think about it like this. All right. Okay, so what are we doing? Okay, so so now in this funny n-dimensional space, now I have to think about those row vectors in an n-dimensional space. In this n-dimensional space, I have one row vector, A vector. I have another row vector, B vector. Okay, I have these 2 row vectors. And okay, that's it. That's what the data is. Now, let's say I go to a different Lorentz frame. In a different Lorentz frame, I'm acting on these vectors with an SL2 transformation. So let's say I go to a different Lorentz frame. Of course, these vectors won't be the same anymore, right? In a different Lorentz frame, I'm going to have some A prime and some B prime, and they will move as I go from one Lorentz frame to another Lorentz frame. But there is something which is invariant. And the reason is that whatever A prime and B prime are, because Lorentz is SL2 cross SL2, but the way it acts on lambdas is just one SL2, A prime is some linear combination, alpha A plus beta B, and B prime is gamma A plus sigma B. So A prime and B prime, these n-dimensional vectors are just a linear combination of the original ones. And so what that means is that while A prime and B prime, while A and B change, there is an invariant. The invariant is the plane that's spanned by them. And so this is the sort of beautiful thing, is that the Lorentz invariant way of talking about this data of the lambdas is not to specify the lambdas individually, but to specify this 2-plane in n dimensions. So there's this 2-plane lambda in n dimensions, okay? And different choices of a Lorentz frame are sort of different bases for this plane. I have this one, I have that one. I can make different bases for expanding things in this plane, but the invariant is the plane itself. Okay? All right, so you see that even whether we and the same thing is true for lambda tilde. Okay, and in fact, the data, the kinematical data look like this. Here's lambda. Here's the lambda 2-plane, and there's another 2-plane, lambda tilde, capital lambda tilde, and I've deliberately drawn it to make it look like these planes are orthogonal to each other, because that's what momentum conservation is. Momentum conservation says that the sum of lambda A alpha lambda tilde A alpha dot equals 0. That just says that the dot product of any vector in this plane with any vector in that plane is equal to 0. And so these 2 planes are actually orthogonal to each other. And so at the most basic level of just thinking about the data for the kinematical data for the scattering process, the kinematical data is given by two planes in n dimensions, and momentum is the slightly non-trivial statement that these 2 planes are orthogonal to each other. So that's why you see, whether we sort of like it or not, thinking about the space of 2 planes in n dimensions is just part of the kinematical data. Now, this is even more obvious if you think about the momentum twistors, because as we've said over and over again, let's do the same exercise for the momentum twistors. So again, the momentum twistors are to begin with are given as Z1, Z2, up to Zn. Okay, but so I can group them as into a 4 by n matrix. But I can also think about them as in exactly the same way as 4 row vectors. And when I do conformal transformation, dual conformal transformations, it just acts on the z's as 4 by 4 linear transformations. So I have one set of 4 vectors, and then in another, after doing conformal transformations, I get another set of 4 vectors. So the 4 vectors themselves, these 4 n-dimensional vectors, they move around, but the plane, the 4 plane now, that's spanned by these 4 n-dimensional vectors, the 4 plane is the invariant. So the momentum twistor data is given by the sort of 4 plane Z, which is a 4 plane in n dimensions. So where is this Grassmannian structure coming from? Why is it relevant for amplitudes? Well, it all goes back to this basic fact that I alluded to in a couple of times early on. There is something special in 4 dimensions that space-time symmetries like Lorentz and like the conformal group look like linear transformations. That's where the connection to linear algebra, planes, twistors, all of this stuff is reflecting that sort of simple, basic, but sort of deep linearity of the action of space-time symmetries. And that's where all this linear algebraic growing into Grassmannian structure ultimately comes from, and why it is at least the first instantiation of why it's relevant. So let me just say a few then general things about Grassmannians, and then we'll take our break. So how do I think about the sort of general Grassmannian GKN? Again, this is the space of K planes in n dimensions. The projective space, P, if you like, n minus 1, is the special case of G of K equals 1 and n, where this is the space of 1 planes or lines in n dimensions. Okay, so that's the sense, just we said at the start, that Grassmannians generalize projective space. But let's just do some very basic things, like how would I label some K-plane in n dimensions? Well, to label, just as we've seen in our examples, I have to give you, so here's my n vectors. I have to give you K vectors. This is the first one, the second one, the third one. Okay, I have to give you K vectors whose span gives me the whole space. Okay, so I give you K n-dimensional vectors. So we'll call these vectors C alpha A. So alpha will run from 1 to K, and A runs from 1 to N. Okay? But if we only care about the plane that's spanned by these vectors, then anything that we do has to be invariant. We have to have invariance under GLK transformations, K by K linear transformations, under which C alpha goes to, again, some general matrix L alpha beta, C beta A. Okay, so the Grassmannian GKN is just the space of K by N matrices, C, modulo the action of GLK transformation on the left. All right, now from here we can very easily see the dimension. What's the dimensionality of GKN? Well, to begin with, I have K by N matrices that have K times N degrees of freedom. So that's just for the matrix C. But I have to subtract K squared, which is the dimensionality of GLK. And so from here I get K times N minus K. Okay, so that's our first sort of very basic thing to learn about the Grassmannian. You'll notice that the dimensionality of GKN is the same as the dimensionality of Gn minus Kn. And that's the very simple fact that there's again, an extension of the duality, the projective duality that we're talking about, is that a K-plane in n dimensions, so if this is the K-plane in n dimensions, then there's a uniquely specified n minus K plane in n dimensions that you can intuitively think about the one which is orthogonal to it. Okay? So a K plane and an n minus K plane in n dimensions specify exactly the same data. You give me a K plane, there's a unique orthogonal n minus K plane, and vice versa. Okay? So that's the duality between planes and their complements is reflected in this formula for the dimensionality. So just as in projective space, in projective space, we just have this GL1 invariance, and we can use that to take my, if I now write things in the same language, I'm now writing my projective. So, P3, for example, I would now be writing in this language as some C1, C2, C3, just writing it as a row vector now. And so I can use this, I can use the GL1, the overall rescaling to, for example, set, sorry. I can use the GL1 to set, let's say C1 to 0. Well, so I can do, sorry, C1 to 1. Well, we can do this in general. So let's do our first interesting example is G24. Okay, that's the G23 is really the same as G13 by the duality we just talked about. So it's not really new. The first new case is G24. So this is again naively, it's well, it is 4 column vectors, but I can use my GL2 freedom to take any 2 of the columns. Let's say the first 2 for fun. I can use my GL2 transformation to just to multiply by the inverse of C1 of the matrix C1, C2. So using GL2, I can set this matrix to be 1, 0, 0, 1, and then the rest is whatever it is, A, B, C, D. Okay. Or I could gauge fix the GL2 another way. I could put the first and the third column to 1, 0, 0, 1, and then have some alpha, beta, gamma row. Okay. So these are all different ways of putting coordinates on G24, which is the analog of setting some coordinate to 1 in projective space. There are just different ways of sort of gauge fixing this the action of this GL2. Finally, we can also talk about forms on Grassmannians. And there's an analogous formula to the XDX formula. I don't have time to describe it sort of most invariantly in detail, but it works essentially exactly the same way. We have to have forms on GKN. They have to be invariant under the local action of GLK. But in practice, in practice, we can write down something you call DKNC for this K by N matrix modulo GLK, and then we multiply this by any function of the C's that has weight minus K times N. In order to make up for the weights that you see there. What this measure is in any gauge fixing is the obvious one. For example, for G24, D2 times 4 C mod GL2 would simply equal dA, dB, dC, dd. Sorry about that. If we do this gauge fixing, any one of them. Okay? So in any one of these simple gauge fixings where you use the GLK to set some K by K block to the identity, then you just wedge together the d's of all the variables that are left. Okay? So finally, a special case of the Grassmannian. See G24. This is the space of two planes in 4 dimensions. So again, I can specify it by giving an AI and a BI, but where I identify AI and BI with any linear combination, right? That's just what it means, up to GL2. So AI and BI and alpha AI plus beta BI, gamma AI plus sigma BI. And of course, that should remind you of something. That was exactly our description of the lines in Twistor space, right? We said it's a line AI and BI, but I can take any linear combination of them to get some A prime and B prime, where A prime and B prime are related to A and B by a 2x2 linear transformation. So you see that G24 is the same as the space of lines in P3, not P3, but lines in P3. And this in turn is the same as space-time, points in space-time, under this Twistor correspondence. Okay, so that's one special example that will of course be important. Okay, so that's it for the crash course in projective geometry. That's really sort of, if you want to sort of think about these things and play with them, that's really like 95% of what you need to know. You don't need to take, any fancy courses or anything. You mostly just play with these very simple linear algebra things. The main thing that you have to get used to is just easily using these brackets and finding intersections of planes and 2 or 3 planes with each other and so on. That's what I alluded to in the beginning of this discussion, that everyone knows what projective space is, but in this business, you have to live there and sort of be comfortable living there. And what I've tried to do in this part of the lecture is tell you everything you need to know to be comfortable living there. And it really is sort of 95% of what you actually need to know to be able to do that. Okay? All right, so let's stop there and take another little break perhaps, and I'll take some questions as well if there are any.
I have a question.
Yes.
So to do the gauge fixing, are you restricting to a specific chart? I mean,
yes,
this one.
Absolutely. It's always the case. All these things are true in specific charts, even in projective space. And so just like projective space, you can cover with charts where you say the top component is non-zero, or this component is non-zero, and so on. The same thing is true for the Grassmannian. You can cover it with many charts in which a particular k by k determinant in the matrix is non-zero. If that determinant is non-zero, then you can restrict there. If it is zero, you have to cover it with another chart. So the whole thing is covered by many charts.
So is this always necessary, like to go to a specific chart to do the gauge fixing, or it can be done in a more general way?
No. I mean, the whole notion of gauge fixing involves that's the point. The whole notion involves choosing a chart. So indeed, that's really the point. These manifolds cannot be covered. They can't be covered by one chart. Of course, even the circle can't be covered with one chart. Which is the point. The circle not being covered by the one chart is the same as P1 not being covered by one chart.
Okay, thanks.
Do we have any other questions? Yeah, I don't see any. Nima, you want to take like a 10-minute break?
Yeah, 10-minute break is fine. Yeah.
Okay, so I guess let's come back on at 15. Yeah, on 15 past what per hour anybody is. And all right, thanks, Nima.
Thanks. Okay, very good. All right, so now we're going to start talking about this in some generality, so that we can use the results later as we need them. This notion of positive geometries and their associated canonical forms. And I'm not going to be very mathematically rigorous here. It's possible to be rigorous. We've written, there have been sort of long papers making all of this more rigorous. But we actually won't need I mean, for some things the rigor is actually useful, but for our purposes today, we won't really need it. So just to say again, what the intuitive idea is that there is some region, a positive geometry. I'll draw it like, I'll draw it so that you can have some curvy sides. So it's not just something like triangles or polygons or polyhedra. But it's some region, P. It's a region, in a compact region in some space. And what's important about it is that it has boundaries of all codimension. So here I've drawn a two-dimensional picture. It has two-dimensional boundaries. It has a two-dimensional picture that has one-dimensional boundaries and zero-dimensional boundaries. Okay? So, so just to begin with, this is a positive geometry. Of course, you know, this is a positive geometry. This is a positive geometry even. Okay, so, right, because it has. But for example, a circle is not a positive geometry just by this definition at the moment. Okay? A circle has just a one-dimensional boundary and no zero-dimensional boundary. Okay. Okay. So that's what we have. We have this. So we have this real geometry P, and associated with it is a unique differential form, omega P, with the property of having logarithmic singularities. And I'll define what that is in a moment, on and only on the boundaries of P. Oh, and by the way, all the boundaries of P are also positive geometries, which are lower dimensional positive geometries themselves. Okay, in fact, you can, there's many ways of thinking about it. Not every possible compact space will have the property that the form is unique, for example. So, it's a definition that the sides go together. That there is some real space with boundaries of all codimension, and the boundaries have the property that the actually important point of the boundaries is that there should be no holomorphic differentials that are defined on the boundaries. If there were holomorphic if there were holomorphic differentials with no singularities that could be defined on the boundaries, then you obviously couldn't uniquely specify the form by requiring that it has singularities on the boundary, because you could add something that's non-singular on the boundary. So there's a few caveats like that. But anyway, you can really think about a positive geometry as some region with boundaries of some compact region bounded by boundaries of all codimension, with no smooth holomorphic forms defined on any of its boundaries, and a unique differential form that has logarithmic singularities on and only on all the boundaries. So now let me instead of giving there's a question here. Yeah, we're once again, all of these real geometries are just thought of as being as sort of, you can think of them as all being embedded in an ambient complex space. And we're definitely talking about polymorphic differentials, which can have poles. So they could be they're allowed to have poles, but they're rational forms on these spaces. But instead of going through generalities, let's just immediately get into an example. Okay, so first let's talk about this notion of logarithmic singularity. What is a logarithmic singularity? Well, it's a real singularity of a form, a singularity that can't be removed by doing a coordinate transformation. So you're familiar with this in just one dimension. Let's say so first here we're having a discussion of logarithmic singularity. Okay, so let's say I have a form, and you say, okay, I have a form like dx, and that seems like a perfectly nice form we call it dz. Okay? That seems like a perfectly nice form, except it does have a singularity at infinity. If I think about this as a form defined on the entire complex plane, including the point at infinity, it does have a singularity there. Okay, but on the other hand, I can always remove that. I can remove that singularity by making this obvious transformation. So dz seems perfectly fine, but dz over z squared seems like it has a pole. But if I write z equals -1 over w, then dz over z squared equals dw. Okay, so these singularities that involve double poles at infinity in this example, they're not really interesting. We can remove them by simple coordinate transformations like this. Okay? The thing that we cannot remove in this way is dz over z. And what is the point? The point is that dz over z squared is really secretly the d of something rational. It's the d of -1 over z. But dz over z is not the d of something rational. It's the d of something that has a branch cut, the d of log z. And that's why I can't remove it. There's something invariant about that singularity at z equals 0. And a more invariant way of saying what that, another way of saying what that invariance is if I do a contour integral of this form, if I do a contour integral dz over z squared around this little circle going around the origin, I get 0. But if I do the contour integral dz over z of this going around the origin, I get 2 pi I. Okay? So these logarithmic singularities are the sort of genuine irremovable ones, and those are the ones that we are. Interested in. So when we say that our form omega has logarithmic singularities, it means that wherever it has singularities, there's locally a choice of coordinates so when I have a D form, such that omega D in the neighborhood of the singularity looks like dx1 over x1 up to dxd over xd. That doesn't mean that I can write it that way globally. Okay, we can have sort of very intricate forms, but everywhere it has singularities, locally the singularities look like the wedge product of a bunch of d logs in exactly this way. And you can therefore take a residue around a singularity of any dimension, not just a point, but practically it means sort of one variable at a time. You can take a residue in one variable at a time and go from a D form to a D-1 form, and that notion makes sense. Okay, so again, instead of going through lots of generalities, let's just jump in immediately to some examples. So our example 1 of a positive geometry is the simplest one, is an interval in one dimension. Okay, so let's say I have an interval. So this direction is z. And here is the point A and the point B. And I want my positive geometry to be the interior of this interval. Okay. Okay. So by the way, right here we see, let me just explain quickly the motivation for the word positive. The positive in the positive geometry is a way of specifying that you're talking about an interior. For example, all of the points in here, every point in here, every point inside, z inside, looks like some alpha A plus beta B over alpha plus beta, where alpha and beta are positive. So in other words, it's a weighted combination of the two vertices at A, of the two ends at A and B, but with a positivity condition. Okay? So that's a very basic thing. We'll be coming back to it a number of times, but specifying the interior of some region involves a notion of positivity. Again, we'll be seeing this in a number of examples. All right. So, but let's now write down what is the corresponding. Let me now erase this. What is the corresponding canonical form? Okay. So, what should omega be? Well, clearly it should have a logarithmic singularity at z equals a. So it should be something like dz over z minus a, and also a singularity at z equals b. So dz over z minus b. But now here's a very important point. There has to be a minus sign between them. Okay? And in fact, this form is only associated, I should have said that P should be orientable. And so this form is defined up to overall sign. It has to do with the orientation. Okay, so I'm breaking the symmetry between A and B because there's an orientation. So for example, tacitly an orientation associated with this interval. But why is there a minus sign there? Well, most naively, you would have thought that there was a plus sign. So what would have happened if there was a plus sign? Well, if there was a plus sign, this form would have a logarithmic singularity at z equals a. It would also have a logarithmic singularity at z equals b, but it would also have a singularity at z equals infinity. As you go to infinity, this form would be 2dz over z, and therefore it would also have a singularity at z equals infinity, a logarithmic singularity at z equals infinity. And the whole point is that we only want this form to have singularities on and only on the boundaries of the space. So we don't want it to have a singularity at infinity. We only want it to have a singularity at z equals a and b, and that's why there's a minus sign. Okay. All right, so that's our first example, and so this is the canonical form for an interval. Let me actually let's right away rewrite this in our projective language. So let's say that I introduced a variable x. I'm sorry for mixing up notation a little bit, but x to be like 1z, to be to projectivize to 1z. So what is our form? Oops. And so I'm going to introduce some point A, which is 1 little a, and B, which is 1 little b. But I just want you to see how nice these forms look, and again, how easy it is to guess what they look like just by writing things down that make projective sense. So what is omega? Omega would be, everything has got to be x dx. Now, we know that it has to have a pole when x goes to A and a pole when x goes to B. Okay, so it has to have a pole when x goes to A and a pole when x goes to B. And again, just by weights upstairs, we have to have an AB. Right? And that's the canonical form for an interval now written in the projective language. Okay? And so we can see that indeed with these with this coordinate choice, this becomes dz. This AB becomes b minus a over z minus a, z minus b, which is exactly what we had above. Okay, now let's do the next simplest example. Let's imagine we have a triangle. And again, I'll just do it with in normal coordinates first. So we just have a triangle like this. So this is so here's x and y. This is the line, let's say 1 minus x minus y equals 0. Okay? So that's x equals 0, and that's y equals 0. Okay, and now let's think about what the canonical form is. Well, again, now it's a two-form, it's a two-dimensional space, it's a two-form. So the form is equal to dx dy over, well, it has to have a singularity when x goes to 0, y goes to 0, and also when 1 minus x minus y goes to 0. So let's just put them all downstairs. And we can again see that this is the right answer for the canonical form, but already this is slightly more interesting. Okay, so let's verify that this form has logarithmic singularities on and only on all the boundaries. And the crucial thing, it has logarithmic singularities on all the boundaries of all dimensions. Okay, so let's see what we mean by that practically. So I want to see what happens, for instance, when I take a residue that puts me on x equals 0. I want to sort of go on this line where x equals 0. Okay, so that means that I want to take a residue of this form. I want to take a residue of omega at x equals 0. Okay, well, what does that mean? You could think of it if you want, that you do a little contour integral around x equals 0. But anyway, in practice, it just means everywhere you see, I just get rid of one of the forms here. This dx over x, I'm taking the residue around x equals 0. And after I do that, the form is only restricted to x equals 0. The form, I take the residue of omega, it only makes sense on x equals 0. And this is equal to what's left, dy over y times, and now x has gone to 0, so it's 1 minus y. Okay, so that's the residue of the form that I get on x equals 0. And now, lo and behold, notice that this residue now it only makes sense on this line, this interval. That interval is a positive geometry, just like we talked about. And what is its canonical form? Its canonical form should be dy over y minus dy over 1 minus y, which is exactly dy over y 1 minus y. In other words, this is the residue, this is the canonical form for, this is omega canonical for the y equals 0, this x equals 0, so we have this surface x equals 0. On the surface x equals 0, this line x equals 0, we have the segment of our positive geometry, which is just that. And what we get from the residue of our two form is indeed that one form restricted with singularities only on now the points. Okay, so, and you can check the same thing for all the other boundaries. So the boundary at y equals 0 and the boundary at 1 minus x minus y equals 0. Okay? In all cases, we correctly get not just that the poles are in the correct place, but after I take the residue on the pole, I get a new positive geometry on the boundary, and I still get the correct lower dimensional canonical form there. All right, good. So let's also work out what this triangle looks like said more projectively. So let's say I give you a sort of random triangle like this, and its corners are let's say Z1, Z2, and Z3. So now these would be given by 3 vectors. And I have some point, I'm going to call the point here, because I'll use this notation later, y. So capital Y is my, capital YI is my variable that sort of lives in the whole projective space. It would be like y1 times some little y vector. What is the form? Well, the form has got to be, it's y dy dy. That's what we always have in projective space. It has to have a pole when y goes to 1, 2. Y lies on the line 1, 2, so it has a pole y 1, 2. and then y23 and y31. And finally, we have to make sense of the overall weights. So there's just involving 1, 2, and 3. There are, you see 1, 2, and 3 occur twice downstairs each. So upstairs I put 1, 2, 3 squared. Right? And once again, if you choose specific coordinates and go to this triangle or any other triangle that we talked about, you'll get the correct canonical form. So this is the canonical form for a triangle, written in projective language. I hope you see how much more elegant and sort of easy it is to think about what these things are doing when you write them projectively, because the form just tells you the story of what it's doing without thinking about it. You see where the singularities are and so on. Right? Okay. Now let's do the obvious next example. Let's look at a quadrilateral. Okay, so here's my quadrilateral. Always the challenge in this subject is that it's hard to draw things without making some lines parallel that you didn't mean to make parallel. Okay, so all right, so here's a quadrilateral whose edges are 1, 2, 3, and 4. And let's this time actually jump to just trying to write the answer down projectively, since it's already sort of intuitive. I'll come back to doing it in some coordinate example in a moment, just directly with the coordinates. But let's see what the form could be. So again, we have some Z1, Z2, Z3, Z4, and I have Y points here. So the form that I want to write down is Y dy dy. And now clearly this form is going to have, poles when Y lies on the line 1, 2, 2, 3, 3, 4, and 4, 1. So it should look like Y 1, 2, Y 2, 3, Y 3, 4, and Y 4, 1. Okay, so could this be the full answer? No, it can't be the full answer for a variety of reasons. First of all, it actually doesn't yet make projective sense, because while I have all these, I have 4 Y's downstairs, there's only 3 Y's upstairs, and so there's something missing upstairs. I need something extra just to carry the weight of the Y's. I need something, the GL1 weight of the Y's. I need to write something that's linear in Y. Okay, so upstairs, there's going to be something that's linear in Y. So there's some sort of special line Y that has to show up upstairs. Let me write it as L-I-Y-I. So we don't know what this L is. But anyway, there's something missing upstairs. But there's a related problem. So let me actually move this. There's another problem, which is that just because while this form so far has guaranteed that I have poles, the first poles where I should when Y goes on the edges, it does not guarantee that if I take another residue that I have the singularities in all the correct places. And let's see why. So let's say I take a residue where Y12 goes to 0. Okay, so if Y12 goes to 0, then that means that I'm localized on this line. Okay? So I take a residue there and I'm localized on that line. Now, but after I take the residue, I still have Y23, Y34, and Y41. I just evaluate these 3 guys. I just evaluate them on the line, on line 1, 2. So in principle, after I take the first residue, I have a 1 form, and that 1 form could have singularities when Y23 goes to 0, Y34 goes to 0, and Y41 goes to 0. In principle, it could have singularities in all those places. Well, let's see what they are. So I'm already stuck on the line 1, 2. where's the singularity where y23 goes to 0? Well, that would be there. That's this line. Good. So where does that line intersect this one? That is this point. That's good. That is a legal point of our geometry. It's point 2. Similarly, what happens when y41? So y23 is good. What happens when y41 goes to 0? Well, that's this line. And that intersects there at the point z1. That's also a good boundary of our positive geometry. But for this line, y23, we have a problem because, sorry, for y34, we have a problem because y34 intersects y34 intersects out here, and that is not a part of our geometry. Okay? So, in other words, if I just write down these poles, I'm not guaranteeing that I'm guaranteeing that all the codimension 1 singularities are correct, all the first boundaries are correct, but I'm not guaranteeing that the next singularities are correct. Remember, that happened kind of nicely in the case of the triangle. We didn't put it in, it just came out, but now it's not guaranteed to happen. Okay? And you can see there's actually 2 bad points. This was my quadrilateral to begin with, but I have this bad point, and I also have an analogous bad point when I go out here. Okay. So said another way, the kind of pattern of intersection of these 4 lines, there are 4 lines, there are 4 choose 2 equals 6 ways that they could intersect. Only 4 of those intersection points are the ones that we want. Only 4 of those intersection points are actually boundaries of the positive geometry. These guys are not, and so we don't want them. Okay? So in other words, we don't want the form to have any residues there. So there's this point which is 1, 2 intersect 3, 4, and there's this point which is 2, 3 intersect 4, 1, and we want omega should have vanishing residues at these points. Okay, and fortunately, it's very easy to do because we also have to specify a line upstairs. So so something has to specify that line, and the purpose in life of this line is exactly, this line up here is exactly the line that passes between these 2 bad points. So that's this line Li that has to appear upstairs. Okay? You see, that line guarantees, that Li guarantees that the residue on both of these bad points is equal to 0. Okay? So we've seen already the case of the quadrilateral is slightly more interesting, right? So I have a geometry that looks like, I have some geometry that looks like this. I keep not drawing this quadrilateral well. So we have these bad points. We just defined this line that passes through them. And so omega canonical is already slightly more interesting. It's y dy dy. And then there's this interesting 1, 2 intersect 3, 4, 2, 3 intersect 4, 1, y. Okay? That bracket upstairs divided by y1, 2, y2, 3, y3, 4, y4, 1. Okay? Okay. So you see, it's already, even in this simple example, we see that specifying this geometric region and demanding that we have a form that only has singularities, logarithmic singularities on this region, already forces a rather more interesting and kind of intricate form associated with it. Okay? So this is a general pattern over and over again. Again, that's the basic thing that converts geometries into forms, and it's the forms that ultimately turn into amplitude. We interpret as the amplitudes, but this is the dictionary that goes from a real geometry and converts it to a form. In fact, it's a complex form that we can think of evaluating anywhere, and is the basic connection between
Could you please explain the notation of the square bracket? Is that?
Oh yeah, sure. Yeah. No, this is not. It's not a square bracket. This is just a 3 bracket between, but between these composite points. So I have to first define the point 1, 2 intersect 3, 4, and then 2, 3 intersect 4, 1, and y. And so you remember we defined 1, 2 intersect 3, 4 is, for example, is Z1, 2, 3, 4 minus Z2, 3, 4, 1, for example. Okay. So we talked about how to see these intersections in our previous discussion. Z2, 1, 1, 1, 3, 4. Okay, so that's 1, 2 intersect 3, 4, 2, 3 intersect 4, 1 has a similar formula. Okay, and so we're just taking the bracket between the 3 bracket between all of these guys. Notice that all the weights work out nicely. The y weights work out nicely. That's what we said before. And also the weights in 1, 2, 3, 4 work out nicely. There is each one occurs twice downstairs and occurs twice upstairs. Okay, now let's do just one more example like this. Let's say we do a pentagon. And this time I'm going to cheat by actually drawing the bad points first. Okay, so here is my pentagon, actually. Okay, so there's my pentagon. I'm interested in this region. That's my positive geometry. So there's my points Z1, Z2, Z3, Z4, and Z5. Okay. And now, once again, I would write down a form. If I wrote down a form, it would be y dy dy over okay. But upstairs, by weights, I need to have something of weight 2 in y. So upstairs, I have to have some kind of conic, Cij, yi, yj. Just by weights. But what should that conic be? Well, in this picture, I have 5 edges. There are 5 choose 2 places that I can have edges intersect. Of those, 5 choose 2 equals 10 intersection points. 5 of them are the ones that I want. They're the vertices of the pentagon. But then I have these 5 bad ones that I don't want. Okay? And so omega has to have 0 residue here. So omega has to have 0 residue on these 5 points. But fortunately, there's a unique conic that passes through those 5 points. Okay, drawing badly. And that's exactly the conic that has to go upstairs. This conic C is the one that appears in that numerator. And so this is already as you see, it's a cooler example. So just saying you have something like a polygon, like a pentagon, for example, the canonical form that goes along with it is not trivial. And here I've essentially directly used the definition of the canonical form, that it's logarithmic singularities on the boundaries of the geometry. And if you just slavishly use the definition, then it's interesting. You have to think to see where the singularities are, and it's non-trivial for the to determine this form. You get an interesting result from doing it. Okay. All right, so let me pause and see if there are any questions about this right now. Yes, there's a question: are the coordinates real numbers? Yes, the way I've drawn it, all these things are real. So this is an important point. So I'll say it again. We even saw it in the first example. We have some real region. We have some real region and a real geometry, like the interval. That was a real interval, but the differential form that's nailed by that region, by having logarithmic singularities. In other words, we have a real differential form on the real space. That real differential form is nailed by the requirement of having logarithmic singularities on the boundary of the space. And that real differential form is then otherwise analytic and is continued to the general complex numbers. So absolutely, all of these pictures are real. There's another question. There's an earlier question I missed. For every D-log form, is there a positive geometry? Likely no. And but there is kind of some sense in which, and this is again an experimental statement, but there is some sense in which in every interesting situation, D-log forms are naturally expressed in terms of a set of objects that are positive geometry, as far as we've seen over and over again in examples. But if you give me a random form with logarithmic singularities, it's not manifest. I mean, it's already non-trivial that it has that property, but it's not manifest that it can come from a positive geometry. And there are many examples where it doesn't. But that being said, there's a sense in which in every interesting example, natural set of objects that you can use to build all D-log forms are all associated with the positive geometry. Another question is, if the boundary is not a straight line, how to express omega? And you have to look at it in a case-by-case example. So I will be talking about cases where we understand positive geometries. We'll be spending some time just here talking about polygons and polytopes. But we will later be generalizing these things to more curvy situations in Grassmannians. So they're not only restricted to situations which are, restricted to situations which are sort of straight. They can definitely also be a curvy. Let me very quickly give you an example of things that do and don't work, because we can see this already in simply in 2 dimensions. So let's say that so here's an example of a positive geometry with a curvy boundary. So just I have a semicircle cut out. Anyway, I have some conic cut out by a straight line. Okay, so this is a positive geometry, but here's an example of something that is not a positive geometry. Let's say I have an elliptic curve. Okay, so I have something that whose equation looks like y squared equals something cubic in x. Okay, so here I started off with a conic and I cut it out there. Here, I'm going to start off an elliptic curve, and let's say I cut it out like this. Okay, so in both cases, it doesn't look too different. The actual geometry, it looks like something curvy bounded by something straight. However, this one is a positive geometry. This is a positive geometry. And this one is not a positive geometry. And why is that? The reason is that in this case, there is actually not a unique form with logarithmic singularities on the boundary of this space. Why not? Because this elliptic curve has a holomorphic differential on it. And so if you give me 2 forms that do have logarithmic singularity on these boundaries, if I give you one form, I can get another form just by adding the holomorphic differential, like dy over x on this elliptic curve. So it's not guaranteed that every shape, everywhere you cut it out, everything is a positive geometry. But there are many examples that go well beyond these polygons and polytopes. In fact, ironically, we first ran into these positive geometries in fancier contexts involving Grassmannians. But in fact, just a simple case where they involve polytopes is already very interesting. When I come to tomorrow to talking about the biadjoint phi cube theory, it'll, in a sense, be much easier and more familiar. We'll just be talking about polygons and polytopes and their generalizations. Okay. Yes. So there's another question. Let's see. Do lower dimensional differential forms, logarithmic state, play some roles for a positive geometry? Well, yes. We can have. First of all, given a positive geometry and its canonical form, as I've stressed, all the boundaries are also positive geometries, and we get the canonical form for those boundaries by taking the residue to go there. So in that sense, we have lower dimensional differential forms, but of course, they're all living on the subspaces associated with the facets. The question of whether they're genuinely lower dimensional forms that we sort of care about, that comes back to this issue that I alluded to in sketching out the sort of grand picture for how these objects live in kinematic space. Ultimately, we're going to be interested in lower dimensional forms that live in a large space, but always to find that they're canonical forms for positive geometries, we have to find some appropriate subspace to pull them back to in order to be able to interpret them as the canonical forms. So we're definitely interested in lower dimensional forms that live in high dimensional spaces, but the connection to a positive geometry, at least in the way we understand so far, perhaps there'll be generalizations, involves finding a space on which the form is top dimensional. All right, another question was, in the particular case of polygons, does this construction of the canonical form extend to arbitrary n-gon? And it does, and it's a beautiful exercise. I'll let you do it for yourself to see how, in this case, literally that simple idea of looking to see where all the singularities are and putting the curve of appropriate degree that passes through all those points, it works just perfect. All right, any other questions about this? Let's see. Yeah, so there's a variety of questions whether we can only define the positive geometry by hypersurfaces defined by linear or quadratic polynomial equations. That's a little too simplistic way of saying it. Certainly on the plane it's true, but more generally, what matters is just a sort of topological property that you should not have holomorphic differentials that are defined on any of the boundaries. And there are much more general situations than can just be described by cutting out with simple by fixed degree polynomial equations. There's also a question that if we allow curved boundaries, it's possible to avoid the bad points. No, it isn't actually. I mean, if you have if the boundaries are curved, the intersections can, in general, happen in even more places. So you have to worry about more places where the intersections can actually occur. And finally, there's a question: do we require positive geometry to be convex? And in all the examples we're looking at here, they look convex. And part of the whole point of this story of the amplituhedron is to figure out what the notion of convexity means sort of more abstractly and more generally, and to generalize beyond these sort of familiar situations. Strictly speaking, just the definition of positive geometry I gave you does not force it to be convex. You can have positive geometries that have all the properties that we want and look like this. You know, even in these simple examples, that we can have positive geometries that look like this. But in many examples, most of the examples that we're interested in, there is some notion of convexity and associated positivity that is going to play an important role. Although it doesn't always look like intuitive convexity, there's some more general notion of positivity and convexity, which is important. Okay, any other questions before we move on? Okay, very good. All right, so now these examples that we talked about on the plane are the examples we talked about on the plane are really the kind of are almost all the examples where you can just literally, by applying the definition of the canonical form, figure out what it is. More generally, this gets to be an increasingly sort of an increasingly difficult game to try to find the geometry and all the intersections and where all the zeros have to be, and so on. So I want to talk about some strategies for determining canonical forms. And I'm going to talk about a few of them. So I think it would be good to talk about most of them in one go, and then we can use them, different ones, as they come up. One of them is triangulation. Okay, so let's see what we're what we mean here. So let's say we go back to my example of the quadrilateral. Okay, and so this is so we already know what the canonical form is for a triangle. So if the canonical form for a triangle is simple, let's say I have a quadrilateral. Well, it's clearly tempting to sort of think of the quadrilateral as sort of triangulated. Think about it as two triangles. Okay, and the claim is that the canonical form for the quadrilateral is actually equal to the canonical form for the triangle 1, 2, 3. Plus the canonical form for the triangle 1, 3, 4. And notice that the orientation is actually important here. Okay, so I'm really orienting it 1, 2, 3, 1, 1, 1, 1, 1, 3, 4. Okay. Now, why might this be true? So this is not quite as trivial as it seems at first. But why might this be true? Well, this omega 1, 2, 3 has logarithmic singularities on 1, 2, 2, 3, and 3, 1. 1, 3, 4 is logarithmic singularities on 1, 3, 3, 4, and 4, 1. So they have logarithmic singularities on all these edges, but each one also has a singularity on this guy. Now, this middle guy is not a boundary of the geometry. That middle guy is spurious pole, which is not there in the omega for the quadrilateral. But crucially, and obviously, that spurious pole cancels in the sum of the two terms. Now, why does it cancel? Well, in order to see whether it cancels or not, let's see what is the residue on the pole when I go to the line 1, 3. From omega 1, 2, 3, when I go to the line 1, 3 equals 0, I get the canonical form for this interval 1, 3. In other words, I'm guaranteed to just get the correct form just for this green line ending on 1 and 3. But that's exactly the same form that I'm going to get coming from omega 1, 3, 4. I'm also going to get the canonical form for 1, 3. Okay? This is the crucial point, is that once you take a residue to go on a boundary, it forgets where it came from. You just get the canonical form on that boundary. It doesn't know about the rest of the shape. It only knows about what the boundary looks like. And furthermore, since the orientation on one side is opposite to the orientation on the other side, if I add them here with a plus sign, I really get the canonical forms with a minus sign for 1, 3, 4 relative to a 1, 2, 3. And therefore, the residue on 1, 3 equals 0. So here I'm talking about the residue on 1, 3, let's say y 1, 3 goes to 0, is equal to 0. Okay. So that's how we get. That's how we can get the canonical form by triangulation. And of course, I don't have to triangulate that way. I can triangulate any way that I like. I can triangulate like this. I can even, I can do horribly complicated triangulations. I could put a point on the inside and triangulate like that. All sorts of ways I could do a triangulation. But in general, and this ends up being true for every positive geometry, that if you can sort of tile the positive geometry by smaller positive geometries in any way, so that they're non-overlapping, so it's an honest geometric tiling, then the canonical form for the full positive geometry is the sum of the canonical forms for the ith component of the positive geometries that I'm covering. So this is P1, P2, P3, P4. Okay. Now let's see if we get let's see how this works in a simple example. So we could just do the example of the quadrilateral, but let me just for fun do the quadrilateral directly in some coordinates. So let me actually make it look like a square. Okay. So let's say here's my quadrilateral at 0, 0, 0, 1, 1, 1, and 1, 0. So here's my positive geometry. Now I've drawn it this way because it's totally obvious just to see in these coordinates what omega is. It's just dx over x1 minus x. It's clearly just a direct product of these two intervals. So dy over y times 1 minus y. And we can also see that this form is the canonical form. We can see it because where are the two bad points? Where are the two bad points? Here, the two bad points are when these lines intersect at infinity and where these lines intersect at infinity. So my bad point is x goes to infinity and y goes to infinity here. But indeed, what is the residue of this form at x goes to infinity? It's 0. What's the residue of this form at y goes to infinity? It's 0. So that's exactly what we want. This form has logarithmic singularities on and only on the boundaries of the square. Okay? But we're saying that we should be able to reproduce this from a triangulation. Okay, so I should be able to find the canonical form for this, let's say for this triangle and for that triangle. And we've already worked out what these are. So the canonical form for this green triangle is dx dy. And then we already said what it is. It's x, y, 1 minus x minus y. Oops. Actually, with my convention here, there's a minus sign. The canonical form for the blue region is dx dy. And that guy has poles at 1 minus x and 1 minus y, and again at 1 minus x minus y. And so when I add them up, this is indeed equal to dx dy over x, y, 1 minus x, 1 minus y, 1 minus x minus y. But from the first term, I get a minus 1 minus x, 1 minus y. For the second term, I get plus xy. And so the numerator becomes indeed 1 minus x minus y over x, y, 1 minus x, 1 minus y, 1 minus x minus y. That cancels, and I exactly get what I want. Okay? So that's just showing you explicitly that this idea of the triangulation works. That I can get the form for the square by adding up the form for the two triangles. Okay. Let me just go back to the questions. There was a question: could there be some overall constant in front of the form? I should have maybe said this at the top already when we talked about the interval. You can say, why didn't I put a 2 or a 3? That's sort of purely conventional, because we defined the canonical form for a point to just be the number plus or minus 1. plus or minus 1 could be any constant that you want, but the important point is the same for every vertex. So what would not work is if you had some form and you took residues, everything looked good, but on one corner, by the time you got to the bottom to a point, you got 2, another corner you got 7. That would not work. So so we define it by definition. All the boundaries are canonical forms. So by the time we get all the way down to the points, we defined that residue to be 1. So that 1 plus or minus 1. So that normalizes the overall. That normalizes the overall form. Okay. There's another question. That what happens is we move these vertices around, and no, indeed. I mean, if you move the vertices around, and it depends. If your definition of the canonical form is the interior of this region, the notion of the interior of the region should make sense. And if you move and they switch around, if you still care about the interior of the region, then it should be given by a different formula with the ordering as gives you the convex region that you want. So on the other hand, but I can say it backwards because this is a special case of the general statement that we define these forms and then we continue them anywhere we like. Let's say you took the form. Let's say that that the z's are such that I have this sort of convex quadrilateral. I define that that's what it looks like, and I get a form that depends on the z's. Now I can take that form and I can now forget about the fact that it came from the z. Now I can move the z's around, and then I can move the z's, I can make them complex even, or I can move them so it has a totally different shape, and I can keep the same form. So the idea is that this form is a very plastic thing that I can take anywhere that I like. But what determines the form is when the z's are in some configuration that gives me the particular quadrilateral. Now it's not just one fixed shape; it's a continuum of shapes. So it's not it's sort of top-dimensional region in the space of all z's. But that's in that top-dimensional region. So this is already, you're seeing the beginning of the kind of story of what I was telling you about. We're looking for in kinematic space. There's some region in the z space of z1, z2, z3, z4. There's some region in z1, z2, z3, z4 space where the z's look like this convex quadrilateral. In that region, there's a form in y that's locked by those z's, by being the canonical form. And then once I get that form, I can do anything I want with it. I can take the z's complex, do anything I want. But there is something important about this region in which the z's are ordered and are giving me the boundaries of this quadrilateral. Okay, so so that's one method is triangulation. Any other questions? Okay. Now let's now go to a different method. This method of triangulation, I haven't told you about more complicated positive geometries yet. In fact, for this discussion, for the rest of this lecture, let's just imagine we're talking about polygons and generalizations to a polytope, which I'll talk about shortly. But here's another. However, this method of triangulation does work for any positive geometry, even these fancier ones. Now I'm going to tell you something that we only know how to concretely make work for the case of polygons and polytopes, and we would dearly love to figure out how to make sense for the amplitude. It's sort of one of the biggest mysterious beasts in this whole business is to try to find the analog of what I'm telling you about for a polygon for these for genuine Grassmannian extension of these things into the amplitude. So that's the fact that the canonical form is actually very closely related to a volume or an area. You'll see what this equals means, equals the volume. The canonical form of a polygon P is the volume, not of P, but of the dual of P. Okay? So this is a very interesting very interesting fact. And let me so this is a loose statement. So let me try to explain what I mean exactly by it. So let's go back to the canonical form of a triangle. Okay. So actually, before doing that, before going back to the canonical form, let me remind you that we had a formula. We had a formula for the area of a triangle. If you remember, going back to our projective geometry discussion, we said that if you had a triangle, now I'm going to call its vertices A, B, and C. If I had a triangle with vertices A, B, and C, and I have some line here at infinity, then the area of the triangle was equal to, said projectively, it was equal to A, B, C squared over, ABC divided by L infinity dot A, L infinity dot B, L infinity dot C. Okay, so that's what we said the area of a triangle was. Now, what if instead of giving me the data in terms of the vertices of the triangle, what if I had given you the data in terms of the side length of the edges? So let's say I've given you the data in terms of this edge 1, this edge 2, and this edge 3. Okay. Well, what then? Well, so in other words, so let's say these things, I'll call them W's here. Let's say this is WA, WB, and WC. So this is WA, WB, WC over L infinity WA dot WB dot WC. All right. So, but now these W's have some, let's say, upstairs indices. Then I want to give you these the edges now in terms of these Z's that have downstairs indices. So Z1 lower I and so on. Okay. Well, how do I do that? Well, it's very simple. I first have to just construct A, B, and C in terms of 1, 2, and 3, but it's sort of obvious what it has to be, right? Now, downstairs, I'm going to have, instead of the point A here, I'm going to have 1, 3. So this L infinity WA will turn into L infinity 3, 1, and then L infinity 1, 2, and then L infinity 2, 3. Okay? And then upstairs, I will have Z1. Sorry, let me write this. Let me write this more nicely. So here I'll have that the area is WA, WB, WC over L infinity dot WA dot L infinity dot WC. But written in terms of the edges, it's Z1, Z2, Z3 squared divided by L infinity Z1, Z2, L infinity Z2, Z3, L infinity Z3, Z1. Okay. Now, this expression should look familiar to you. This looks an awful lot, almost what we have for the canonical form of a triangle. But so what's going on? So so here's the picture. So let's go back to our triangle to begin with. So here's our triangle. So here's Z1, Z2, and Z3. And just for fun, I'm going to draw Y inside here somewhere. Okay. And here we said that the form was Y dy dy times Z1, Z2, Z3 squared over Y Z1, Z2, Y Z2, Z3, Y Z3, Z1. Okay. But let me now draw the dual of this picture. So this is the canonical form. Let me now draw the dual of this picture. So the dual of this picture, so by dual, I mean I'm going to interchange points for lines and lines for points. Okay? So that means that Z1 in the dual is going to be an edge. A line, Z2 is going to be a line, Z3 is going to be a line. And now, interestingly, Y2 used to be a point, but now Y is going to be a line. And in fact, if Y was a point inside the triangle before, just for fun, Y will be a line outside the triangle. So you see that the sort of data of the problem is exactly like thinking that Y is specifying a line at infinity. So what? And then I have a triangle now with the edges given by Z1, Z2, and Z3. And you notice that, of course, there's this y dy dy. There's that part of the form that's there in any projective space. But remarkably, what multiplies it is just the area of the dual triangle. So if this is the triangle T, it's the area of the dual of the triangle where y takes the point, where y plays the role of the line at infinity. So y is line at infinity. Remember, to define the area, we needed this notion of line at infinity. Okay. Okay. Now, so that actually extends. That actually extends to any polygon or any polytope. The canonical form for polygon P, let's say, as a function of y is in any number of dimensions. So if we is equal to, well, first there's the y dn y, which is always there, but then what it multiplies is the volume of the dual of the polygon or the polytope, where y is the plane at infinity. So that's a very beautiful and invariant characterization of what this canonical form is. You don't have to triangulate. You have to do anything. There's just a sort of an invariant picture of what the canonical form is, as associated with the volume, not of the polytope or the polygon, but of the dual. Okay, so this gives some extra understanding for why it is that that these canonical forms can be computed by triangulations, and why they have this additive structure. They're kind of like volumes. In fact, they're the duals to volumes. This picture also suggests that it's another way of understanding why you can compute the canonical forms via triangulations. In fact, there's a very pretty and general point that together, if I have a polytope, polyhedra, higher dimensional generalizations are called polytopes. We will define them more carefully, but let's just even talk about polygons for a second. If we have a polygon P, if you give me a triangulation of P, it gives forward and backward a triangulation of the dual. Okay, so this is a slightly interesting thing. Let me show you how it works. So so let's say, for example, here is P. Okay, so here is P. Here is P itself. So it has vertices 1, 2, 3, and 4. And let's say I'm going to triangulate this like that. Okay. Now, what does this look like in the dual? What this looks like in the dual is the following. I have So if this is 1, 2, 3, 4, now I have the edges 1, 2, 3, and 4. But in here, what looks like this triangle plus this triangle, and I'll leave you to just play with this to convince yourself that this is true. What looks like this triangle plus this triangle. So here it looks like I have the triangle 1, 3, 4 plus the triangle 1, 2, 3. But up here, that actually looks like this big triangle 1, 3, 4. This big triangle 1, 3, 4. And then I subtract from it this triangle 1, 1, 2, 3. So in all cases, this is our quadrilateral. We have a quadrilateral, okay? But we're triangulating this quadrilateral in two different ways. A triangulation of the polygon induces a triangulation of the dual of the polygon, and vice versa. Okay? So since we can compute the volume of the dual of the polygon just by adding up the volumes of individual triangles, then when I dualize back, that tells me that the canonical form is what I get from summing up all the triangles. And so the interesting thing is that what looks like a normal triangulation on one side will look like an inclusion-exclusion type triangulation on the other side. But anyway, this is one of the common themes in this business, is that it's sometimes interesting to look at the object and the dual of the object, and natural triangulations of the object make some things manifest, and natural triangulations of the dual often make other things manifest. So, so this is another nice picture for what the canonical form is. That's valid for polygons and polytopes more generally. I'll use it to make one final comment. Let's sort of go backwards. So let's say that this is what the dual looks like. So let's say this is what P dual looks like. Then there's a very natural triangulation of P dual where you don't have to think too much. Just put a point in the middle here, and just draw lines out. Okay. So this is a natural triangulation of P dual, just summing of all of these triangles. What does this look like as a triangulation for P? Well, as a triangulation for P, I get some quadrilateral like that. But this point in the middle is some line outside. I can think of it as some line at infinity, it's some line outside the quadrilateral. And so what does this triangulation of P dual look like in terms of a triangulation of P? It's the following cool picture. You see here, I have something that involves every edge of the dual, so every edge of the dual, and this point. So what does that mean here? It means that I have to draw a triangle that involves every vertex of the dual and this line. So how do I do it? Well, I take this vertex and I stretch it out so it meets the line. That gives me a big triangle. I do the same thing with each one of the vertices. Okay? I do the same thing with each one of the vertices. And now again, I get an sort of inclusion-exclusion triangulation of the interior here by thinking about it as this large triangle minus this triangle. This large triangle minus this triangle, and then I double counted this one, so plus that triangle. Okay, so what looks like a kind of normal internal triangulation here is this interesting triangulation where every triangle in the triangulation is anchored to this line at infinity, and every triangle emanates from one of the vertices. We'll actually talk about generalizations of these canonical forms for general polytopes, but just to say it now, this method of triangulating polytopes, this method of getting omega canonical works actually for any polytope. Just think about them as higher dimensional versions of polyhedra, which has the property of being simple. Called simple And simple means that at every vertex, it locally looks like a simplex. In other words, if it's an n-dimensional, polytope or d-dimensional polytope, there are exactly d facets meeting. At every vertex. Then the formula for the canonical form is simply that you just sum over all the vertices, and we've already seen that every actually, well, okay, let me not say more than that. Just keep that in mind. We will come back to talking about some interpretations for that sort of rather general triangulation in other situations. Okay, any questions about this? How are we doing for a time, Song or Yuten? Should we be wrapping it up now, or what's the deal?
Yeah, I think yeah, we should probably start wrapping up.
Okay.
Yeah.
All right. Good. So then, okay, fine. I will. Maybe I'll just make one more comment then, if we're going to wrap it up here, because I forgot to say it earlier. Then I can actually complete what I just wanted to say. So I should have said this. Earlier. Let's go back. Let's say to the canonical form for the interval. I'm going to tell you something about the canonical forms for. So here we said that the canonical form was dx over x minus a minus dx over x minus b, right? So we can also write this as the d log of x minus, of x minus a over x minus b. Okay. Okay. In other words, this makes it manifest that it has logarithmic singularities. Now, if we write this in terms, if we just write it projectively, we would say that this omega, which was, let's say in this notation, would be y dy over ya yb ab. That this is actually the d log of ya over yb. And similarly, if I go to a triangle, the form is d log of y12. It's a two form, so it's a d log of the ratios. I can put any one that I want to be the last one, to be the one in the denominator. So I could have put 1 3 or 1 2 or 2 3. And that's what the canonical form is. Okay. So you can actually see even in these examples that I can also write this. I can write this form as if I wrote down the sort of linear equations that cut out each side. So if I just go back to normal coordinates. If I just write down the linear equations that cut out each side, like L12, L23, and L31, that this omega is the expression that I was just telling you about before even applies to a triangle. I mean, we could triangulate the triangle by putting some line at infinity and extending the triangles from each vertex. And so that expression just tells me this is d log. I go to every vertex and I just write the d log of the linear equations that cut out the edges that meet at that vertex. So I write down d log L12, d log L31, for example, and then I write down the other one, plus d log L23, d log L31, plus, and so on. Okay, so I have 3 terms, L23, d log L1, 1, 2. And in fact, in general, there's a sign in front of every one of these things that's inherent orientation, and the sign is just given. You see, in the neighborhood of every vertex, these facets have some normals. The normals just show up in the equations for the L's. Okay, so in other words, if each L looks like A dot X plus some constant B, then each one of these normals, this would be like A for 3, 1, this would be A for 1, 2, and so on. So in general, for any old polytope, in the neighborhood of, for any old simple polytope, in the neighborhood of some vertex, there's a bunch of linear equations Li that look like A dot the ambient coordinates X.
Lost your screen.
Oh,
you lost your screen.
Let's see what happened. I'm not sure why we lost the screen. Yeah. So if I take any old polytope in the neighborhood, any old simple polytope in the neighborhood of some vertex V, I'm going to have a bunch of linear equations L1 through LD, each one of which look like, each one of these LIs looks like some AI dot X plus BI. And so to get the canonical form for the whole polytope, I just sum over all the vertices. So whatever this guy is, whatever it is, I sum over all the vertices of the d log of the wedge of the d log of all the Li. So d log L1 dot the d log LD. But I need to have a sign, right? And what could the sign be? What could the sign be? Well, nothing is working here. Well, the only thing that makes sense, it also has to have the data of these L's. It knows about the orientation of each one of these simplices. It's just multiplied by the sign of the determinant of all of these normal vectors. And these AIs are the normal vectors. So A1 up to AD. Okay. So conceptually, at least for these polytopes that are simple, this gives us a nice, conceptually what we had, the simple understanding of what it was the dual. In the dual, so we can also understand why it's important that it's simple from the dual perspective. In the dual, the fact that this polytope is simple, the fact that at every vertex I have D faces meeting, in the dual, it means that every vertex now turns into a face of the dual. So it means that every face looks like a simplex. Okay? So that's why it's as simple as possible. Because every face looks like a simplex, when I put that point in the middle and I draw the lines out to every facet, that covers the entire space. But each one of those pieces is just a simplex. And so that's an extremely simple thing that you can do. It only works when all the facets of the dual are simplices, which is the same as saying in the original polytope that at every vertex you have you locally have something that looks like a simplex. And in that situation, the picture of the volume of the dual then also gives us this formula for the canonical form of the actual polytope. So I haven't yet talked about polytopes in a detail, but I hope this last bit was at least was impressive. You understood what the conceptual point is. This method of thinking about what the canonical form is will have some nice interpretations when we talk later about the biojoint biductive. Okay. Now, so next time, tomorrow, I'm going at roughly half speed, as usual with these things, but tomorrow, what I'd like to do is complete this discussion of positive geometries and canonical forms, and then we will talk about the story of amplituhedra, and And then after that, we will transition to talking about these biadjoint phi cube theories, where the positive geometries are much simpler. I mean, they're conceptually much simpler to start thinking about. They're just polytopes. But while much of the qualitative story is the same, the general structure is the same, the sort of details are very different, and the structure of the kinematic space is quite different as well. Okay, so I'll stop there and I'll ask if there are any questions about this last bit.
Okay, thanks, Nima. If you have any questions, you can raise your hand or unmute yourself if you're able to. So we have some questions in the chat, Nima.
Okay. Okay, so there's a final question. Is there a way to compute the volume of the dual polytope in terms of the volume of the original polytope? No, and in fact, you see, this is a good projective. This is a good exercise of your projective muscles. The notion of a volume needs a privileged plane at infinity. Okay? Now, what we're doing when we compute a canonical form is that we're looking at the form as a function of a point in the original space. So we have some point y in the original space, there's some z's, there's something that's defining this region, and we're looking at the form as a function of, in the y coordinates. There's no notion of a volume we can talk about. To have a volume, you need to have some privileged hyperplane at infinity. There is no privileged hyperplane at infinity there. The interesting thing is that that form is actually equal to this universal form part that has to be there for any form, this y dy dy. After I factor that part out, what's left is just a function of y. And now I can interpret that as the volume of the dual. The volume is a function, it's a number. The form is a form. The volume needs a hyperplane of infinity. That doesn't exist in the original space. But after I decide to strip off this y dy dy part, what is left is depends on y as the point. Now I can imagine dualizing everything. When I dualize everything, y becomes the hyperplane at infinity, and now I can talk about a notion of volume attached to that with the y as playing that privileged role. Now, one thing that is cool though is you can take, for example, that picture that we had for polygons. We gave this picture where to determine the canonical form, you find these bad points and you put a conic that goes, or a curve of appropriate degree that goes through all the bad points. That gives a brand new formula for the area of polygons. Something as ancient as the area of polygons. That's actually a new expression for the area of polygons. We have to interpret it by its dual. So if you want the area of a polygon, you take the dual of the polygon, and then you find the canonical form for that dual polygon by finding this degree k curve that goes through all the points and so on. So this correspondence between canonical forms and volumes is non-trivial. It's interesting. As I said, it's a wonderful fact about polygons and polytopes. We would love to have such an understanding for what the canonical forms of amplitude are, which I haven't talked about yet, but you'll see them tomorrow. We don't have the analog of that. We're missing an analog of the dual of the amplituhedron, and that is one of, as I said, it's a beast that that many of us are absolutely sure exists, but it's been haunting our thoughts and our work for the past 5 or 6 years. I think I'm absolutely positive that it exists, and I think it will be a major development in the subject if we found it and understood. Yeah, and I think the rest of the questions have either been answered or yeah, I think that's all I see on the chat. Are there any other questions?
May I ask a question?
Yes.
Yeah, so in the case of area, when you went to the dual space, what is the motivation of saying that the two area are equal? I missed. I mean, the two area in the original space and in the dual space, you equated them. I mean, oh
no, I'm not saying the areas are the same. No, I mean, as I said, even the notion of area is not the same. I'm just saying that a triangulation of the polygon induces a triangulation of the dual polygon. That is what I meant. And that's something that you should just play with in examples to be convinced that it's true. I mean, all the data matches, you know, we have exactly the same information on both sides, but it's interesting that when you triangulate a polygon, what you get is, like when you triangulate a polygon with just things on the inside, you induce a triangulation of the dual polygon with things on the outside. And it's kind of obvious. Like if I take the triangulation of a polygon where I don't introduce any new points, I just use the vertices of the polygon, then in the dual, I'm going to have a triangulation where I don't introduce any new lines. So it can't look the same, but I get a triangulation on both sides. And I just drew quickly an example of how it worked with a quadrilateral. If you're curious, I would encourage you to just draw some pictures and convince yourself that it actually works like that in general. But it's not that the areas are the same, or they're not. It's just that the triangulation on one side maps to a different triangulation on the other side.
Okay, thank you.
Okay, do we have any other questions? Okay, I don't see anything new in the chat. Okay, all right. Thanks, Nima. I guess this is it for today.
All right, I'll see you guys tomorrow then.
Okay.
Thank you very much, Nima.
It's
such an incredible long marathon. Thanks a lot.
See you guys later.